The universe contains objects so extreme they defy conventional physics, where matter achieves densities of 10 to 18 kg/4, magnetic fields reach 10-15 Gauss, and space-time itself ruptures into singularities. These cosmic anomalies represent the boundaries of our theoretical frameworks, where general relativity and quantum mechanics collide in ways we're still struggling to comprehend. Today we begin with perhaps the most famous of these extremes: black holes, those regions where gravity becomes so intense that even light cannot escape.
We've made them our cultural shorthand for the inescapable, those voracious metaphors that devour lost time, vanished money, the relationships that consume us entirely. From Nietzsche's famous warning that the abyss gazes back, to cinema's depiction of black holes as both perilous doom and transcendent passage, we've woven these cosmic phenomena into our vocabulary of extremes. Yet how extraordinary that what began as pure mathematical abstraction, John Michel's 1783 calculation of a dark star so dense that light itself could not escape, has emerged as perhaps the most verified and observable reality in our universe. The metaphor, it turns out, was never metaphorical at all.
The precision is remarkable. Michel's calculation essentially derived the Schwarzschild radius, r is equals 2 gm per sequar, 2 centuries before we had direct observations. Today's Event Horizon Telescope measurements confirm his math with extraordinary accuracy. Sagittarius A has a mass of 4.15 million solar masses, giving it an event horizon radius of roughly 12 million kilometers. The EHT resolved a shadow 50 microarcseconds across, exactly matching general relativity's predictions for that mass at 26,700 light-years. M87's supermassive black hole at 6.5 billion solar masses produces a shadow 42 microarcseconds wide, consistent with an event horizon spanning 120 astronomical units. The mathematics that seemed impossibly abstract has become our most precise tool for measuring cosmic extremes.
Here unfolds perhaps the most revealing chapter in the annals of scientific resistance. Einstein himself, the architect of the very equations that predicted these cosmic monsters, spent decades denying their possibility. In his 1939 paper, he argued with characteristic elegance that nature would simply forbid such singularities, that some unknown mechanism must prevent matter from collapsing beyond the point of no return. The father of relativity, confronted with his own theory's most extreme implications, essentially declared them too extreme to exist. One wonders what psychic discomfort drove this rejection. Was it aesthetic revulsion at infinity, or perhaps the deeper human need to believe that the universe maintains some fundamental reasonableness, some boundary beyond which even mathematics dare not venture?
Einstein's error was computational. His 1939 paper assumed spherical symmetry would break down during collapse, that rotating matter couldn't maintain conditions for singularity formation. But Chandrasekhar had proven him wrong by 1930, showing stellar cores above 1.4 solar masses must collapse regardless of rotation. Einstein refused to accept this. The deeper issue was conceptual. He couldn't reconcile smooth spacetime with the discontinuous jump from matter to void at an event horizon. His own field equations handled this transition perfectly.
Behind that computational precision lies one of science's most wrenching human tragedies. Picture young Subramanian Chandrasekhar in 1930, barely 20 years old, calculating aboard a steamship bound for Cambridge and discovering that stars above 1.4 solar masses must collapse into something unprecedented, something that would later bear his name. But when he presented this revolutionary work to the Royal Astronomical Society, the Empire's most celebrated astronomer, Arthur Eddington, rose to deliver a crushing rebuke. "I think there should be a law of nature to prevent a star from behaving in this absurd way." The audience erupted in laughter. Here was colonial prejudice masquerading as scientific skepticism, the white establishment refusing to accept that a young Indian mathematician had glimpsed deeper into cosmic mechanics than their revered authority. Chandrasekhar, publicly humiliated, would spend decades in exile from his homeland, vindicated only when stellar corpses began revealing themselves exactly as his equations predicted.
Chandrasekhar's calculation was devastatingly simple. When electron degeneracy pressure fails at 1.4 solar masses, the Chandrasekhar limit, nothing remains to halt gravitational collapse. The mathematics Eddington ridiculed has become our most precise tool. The Schwarzschild radius Rs equals 2 gmc squared scales linearly with mass, giving us 3 kilometers for a solar mass black hole, 12 million kilometers for Sagittarius A. Today's Event Horizon Telescope measurements confirm these predictions to extraordinary precision. M87's shadow diameter of 42 microarcseconds matches exactly what general relativity demands for 6.5 billion solar masses at 55 million light-years. The numbers that seemed absurd in 1930 now anchor our understanding of cosmic extremes.
How curious that we've performed this extraordinary act of mathematical domestication, taking the most violent, incomprehensible phenomenon in the universe and rendering it into neat equations, precise measurements, angular diameters expressed in micro-arcseconds. We've made infinity manageable, turned the ultimate cosmic mystery into something we can calculate and predict. Yet the moment we add a single complication, rotation, the elegant simplicity of Schwarzschild's solution gives way to geometries so complex that even Einstein retreated from their implications. Does this mathematical mastery represent genuine understanding, or have we simply learned to measure our ignorance with ever greater precision?
Rotation destroys the spherical symmetry that makes Schwarzschild geometry tractable. The Kerr metric introduces the dimensionless spin parameter m, which can approach unity for maximally rotating black holes. Real astrophysical black holes routinely spin fast. Cygnus X1 has a ZAS 0.97, meaning it rotates at 97% of the theoretical maximum. This creates frame-dragging effects where spacetime itself gets twisted into motion, and an ergosphere outside the event horizon, where even light must rotate with the black hole. The mathematics work perfectly, but they describe a reality where space and time lose their intuitive meaning entirely.
Indeed, when space itself becomes a whirlpool dragging everything into its spiral, we confront the profound inadequacy of our terrestrial intuitions about the stage upon which existence unfolds. Near the event horizon, this warping reaches such extremes that time and space literally exchange their roles. What we once understood as the immutable flow of temporal sequence becomes as malleable as spatial dimension, while spatial coordinates become as fixed as moments in time. Here, gravity doesn't merely bend space, it transmutes the very categories through which we comprehend reality.
The mathematics become extreme near the horizon. At twice the Schwarzschild radius, time runs at 71% the rate of distant observers. At 1.1 times the radius, barely outside the event horizon, clocks slow to 31% of normal speed. For Sagittarius A, an astronaut hovering 1.3 million kilometers above the horizon would experience 1 hour while Earth experiences 3.
These numbers carry an almost liturgical precision, time itself stretched into ratios that sound like sacred mathematics. What transforms this from theoretical exercise into tangible reality is how recent observations have elevated these once abstract calculations into the realm of direct measurement, turning Einstein's reluctant predictions into our most precisely verified cosmic phenomena.
EHT measurements provide extraordinary precision. M87's first-time shadow diameter of 42 microarcseconds corresponds exactly to a Schwarzschild radius of 120 AU at 55 million light-years, matching a 6.5 billion solar mass black hole. These numbers vindicate decades of mathematical predictions with microscopic accuracy.
Just when we thought we'd grasped these cosmic devourers, Stephen Hawking delivered a revelation in the 1970s that transformed black holes from eternal prisons into slowly dying entities. Through quantum effects at the event horizon, he showed that black holes actually evaporate via thermal radiation. But here's where the universe seems to mock our understanding of causality itself. If information about everything that falls into a black hole is lost forever when it finally evaporates, we're left with a paradox that strikes at the very heart of determinism. Does the cosmos truly forget, or does it preserve every detail in ways we cannot yet fathom?
The mathematics are stark. Hawking radiation temperature scales as Th 6.2 10^-8 times solar mass divided by black hole mass in Kelvin. A 10 solar mass black hole radiates at 610 to 9 K, utterly negligible against the cosmic microwave background's 2.7 K. The evaporation timescale follows Ta 2 10 667 m at Lacru years. Even our sun as a black hole would persist 10 to 57 times longer than the universe has existed.
Which brings us to perhaps the most unsettling implication. If information can genuinely vanish into the void, we're confronting the possibility that the universe itself might not be as rationally ordered as we've assumed. The very notion that causes might exist without recoverable effects threatens the philosophical bedrock upon which scientific determinism rests. Are we witnessing the universe's capacity for genuine erasure, or merely discovering the limits of our conceptual frameworks when pressed against such cosmic extremes?
Holographic principles suggest information maps to the event horizon's surface, preserving quantum unitarity through boundary encoding. But proving these invisible objects exist required detecting their gravitational signatures, mass concentrations so dense they warp spacetime into unmistakable observational signatures. The precision required is staggering. LIGO measures gravitational wave strains of 10 to 21. That's detecting a change in a 4-kilometer arm length equivalent to 1,000th the width of a proton. When two 30 solar mass black holes merged 400 megaparsecs away, producing GW1914, we caught the whisper of spacetime itself flexing by that impossible margin.
Consider the profound reversal. We've learned to hear the universe's most silent mysteries. These gravitational whispers from cosmic cataclysms that occurred millions of years before human civilization existed, now decoded by instruments that stretch reality's fabric to measure distortions smaller than subatomic particles. Through such ingenious indirection, we've transformed the ultimate void into our most eloquent cosmic messenger.
The temperature contrast is staggering. Stellar black holes are colder than the cosmic microwave background at 2.7 Kelvin, making them net absorbers rather than emitters. Yet microscopic primordial black holes with asteroid-like masses would radiate at trillions of degrees. The evaporation timescales defy comprehension. A solar mass black hole requires 1067 years to disappear, 1057 times longer than the universe has existed.
These timescales render even our most expansive notions of eternity quaint. Black holes will persist, not merely beyond the death of stars, but beyond the fading of galaxies themselves, becoming the universe's final torchbearers in an era when space has stretched so vast that neighboring particles drift light-years apart. In their patient endurance through deep time, and their revelation of reality's most fundamental extremes, black holes serve as both prologue and epilogue to the cosmic story, teaching us that the universe's most violent phenomena often emerge as its most enduring monuments. They beckon us deeper into a cosmos where every extreme we think we've grasped merely unveils stranger territories ahead.
Neutron stars exist at the knife's edge between matter and oblivion. A single teaspoon weighs 5 trillion kilograms, 900 Great Pyramids compressed into something you could hold in your hand. Their densities reach 3 to 6 times 10 to the 17th kilograms per cubic meter, with central pressures of 10 to the 34th pascals. That's 10 to the 19 times atmospheric pressure. These objects balance on the ultimate physical threshold. Quantum mechanical pressure from degenerate neutrons barely holds against gravity's relentless compression. Add just a bit more mass and they collapse into black holes.
Yet despite this crushing density, these stellar corpses spin with velocities that shatter intuition. PSR J7482446D rotates 716 times per second, its equator racing at nearly 25% light speed. Consider the contradiction. Matter compressed beyond recognition, atomic structure obliterated into cosmic paste, yet pirouetting with the grace of a demented ballerina. We associate density with sluggishness, mass with immobility. But here are the universe's densest objects, save black holes, performing rotational gymnastics that would tear planets apart. Perhaps the cosmos delights in confounding our earthbound expectations, showing us that at the extremes, familiar rules dissolve into something far stranger.
NICER has achieved unprecedented precision. Neutron star radii measured to within 800 meters from thousands of light-years away. PSR J074 plus 6620 at 2.1 solar masses has a radius of 12.4 kilometers, while PSR J030 plus 0451 at 1.4 solar masses measures 13 kilometers. These measurements reveal the exact pressure-density relationship at matter's breaking point. We see pressures of 3 to 4 times 10 to the 34 pascals at densities around 10 to the 14 grams per cubic centimeter, the precise threshold where matter chooses between neutron star existence or black hole collapse. More massive neutron stars being slightly smaller confirms a stiff equation of state. Pressure rises sharply with density, preventing collapse even at extreme rotation rates.
Such precision both unsettles and illuminates. 800 meters uncertainty across thousands of light years. We've gone from wondering if these objects existed to measuring their circumferences with suburban surveyor accuracy. We've located nothing less than matter's final fortress against oblivion. 3 to 4 times 10 to the 34 pascals marks the universe's ultimate boundary. Beyond this threshold, no force in nature can resist gravity's hunger. We've mathematically pinpointed the edge of existence itself, where being surrenders to not being. For millennia, philosophers pondered where substance yields to void. Now we know with decimal precision. Yet somehow reducing this cosmic boundary to equations makes it more mysterious, not less.
PSR J's 740-6620's 2.14 solar mass validates decades of theory. Between 2.1 and 2.5 solar masses, no equation of state generates enough pressure to prevent collapse, the TOV limit in action. NICER's radius measurements complete the picture. Smaller radii for more massive stars show internal pressure ramping up exponentially near the threshold, but there's a hard ceiling. At 2.14 solar masses, we're already pushing fundamental limits. Add more mass and space-time surrenders. Abstract theory becomes measurable reality. The universe's breaking point sits at 10 to the 35 pascals. Beyond that, only black holes can exist.
From ancient questions about substance to knowing that existence has a mathematical boundary, 10 to the 35 pascals, beyond which being ceases, the precision collapses distance between cosmic and comprehensible. We're taking rulers to reality's edge, finding not mystical thresholds but numbers. Yet here's the deeper mystery. These objects, balanced between existence and oblivion, somehow become the universe's most dynamic performers. Spinning hundreds of times per second, broadcasting across the galaxy with metronomic precision. How does matter at its absolute limit express such exuberance?
NICER's data explains the paradox. PSR J748-2446 AD's 716 rotations per second work precisely because it's near the collapse threshold. At 25% light speed, equatorial centrifugal force reaches 10 to the 12 meters per second squared, enough to tear normal objects apart, but surface gravity hits 10 to the 13 meters per second squared, 10 times stronger than the centrifugal force. The equation of state shows internal pressure gradients can support this configuration because strong nuclear forces bind matter so tightly that even relativistic rotation can't break it. These objects exist in a narrow window. Degeneracy pressure prevents collapse while allowing rapid spin. Exceed the mass-shedding limit, and the star flings matter from its equator. Physics at the absolute edge of possibility.
The universe saves its most spectacular performances for matter's final acts. Here we find not mere survival at annihilation's edge, but relativistic pirouettes broadcast with millisecond precision. Matter confronted with mortality responds with exuberant vitality, extreme compression enabling rather than crushing dynamism. But how do we grasp nuclear density? A teaspoon weighing 900 Great Pyramids represents complete breakdown of intuitive understanding. How does physics describe states where atomic structure surrenders, where our concept of material ceases to apply?
At nuclear density, 3 times 10 to the 17 kilograms per cubic meter, atomic physics breaks down completely. Empty space gets crushed from atoms. Electrons pressed into protons create neutron fluid where particles touch, held apart only by Pauli exclusion and nuclear repulsion. Jocelyn Bell's 1967 discovery becomes even more remarkable. She detected these extreme objects not through exotic density signatures, but through radio pulses so regular, exactly 1.33 seconds, that she labeled them LGM1 for little green men. The universe's most compressed matter announced itself with atomic clock precision. A graduate student with wooden posts and wire mesh detected matter at nuclear density spinning in space. Those scruff marks on chart paper marked humanity's first contact with physics at 10 to the 15 grams per cubic centimeter.
How bitter the irony echoes through Bell's discovery. She catalogued scruff on miles of chart paper and found objects defying comprehension, matter making diamonds look like seafoam. Her first thought, perhaps civilizations broadcasting from the void. Something beautifully human about confronting extreme physics and wondering if someone's saying hello. 4 pulsars in 2 months through sheer diligence, she heard collapsed stars' heartbeats first. Yet the 1974 Nobel Committee honored the supervisor, while the actual discoverer remained unrecognized. Bell's later gesture speaks louder. $3 million donated to support those the establishment overlooks. This moment captures humanity's finest and most flawed aspects. Wooden posts detecting the universe's most precise clocks, graduate student attention unveiling matter's edge, then credit flowing upward while discovery flows from below. Brilliant enough to detect nuclear density in space, yet stumbling over basic fairness.
Bell spent months distinguishing cosmic signals from terrestrial interference. She knew every noise source, police radar, bad thermostats. When that 1.33-second pulse appeared at sidereal time, she recognized it as cosmic, while others blamed equipment failure. These LGM signals became precision instruments when their stability exceeded atomic clocks. PSR B937 plus 21 keeps time to 15 decimal places. We predict pulses years ahead with nanosecond accuracy. That regularity let Hulse and Taylor prove gravitational waves exist by measuring orbital decay to 0.2% precision, decades before LIGO. Bell's scruff marks became cosmic chronometers. We now use millisecond pulsar arrays for nanohertz gravitational wave searches, detecting spacetime distortions of 1 part in 10 to the 15. The universe's densest matter became our most sensitive gravitational wave detectors.
From scruff to precision cosmology, from suspected alien calls to cosmic clocks, perhaps astronomy's most elegant arc. Joy Division immortalized CP 1919's pulses on their album cover, jagged peaks becoming post-punk icons. But those peaks represent deeper truth, humanity transmuting confusion into comprehension, inexplicable into instruments. Bell heard what seemed like messages from other civilizations, and she was right. These were messages, not from intelligence, but from physics itself, declaring, here are the universe's boundaries, where matter makes its last stand. Her little green men became the metronome measuring spacetime's fabric. From wooden posts detecting nuclear density to hunting gravitational waves from colliding galaxies, this trajectory reveals human curiosity's essence. We transform the universe's most violent compressions into tools of exquisite precision.
Bell's methodical patience now lets us detect gravitational waves with amplitudes of 10 to the minus 25, space-time distortions smaller than proton widths across kilometers. Using timing residuals from neutron stars, she first called anomalous scruff. Millisecond pulsars drift less than 1 microsecond yearly, more stable than atomic clocks over decades. Monitoring arrays detect gravitational waves stretching space by 1 part in a quadrillion, ripples from supermassive black holes merging billions of light-years away. Bell's careful signal-noise discrimination became precision astrophysics template. Extreme physics announces itself through regularity, not chaos. The universe's most compressed matter became our most sensitive spacetime probe.
The symmetry between Bell's journey and her discovery runs deep. Both began as dismissed outsiders, becoming transformative forces. She transmuted Nobel's snub into something more lasting than medals. $3 million ensuring other scruffs might be recognized for their true worth. Just as pulsars evolved from suspected alien beacons to reliable timekeepers, Bell evolved from unrecognized student to champion of the overlooked. The same attention, distinguishing cosmic signals from noise, she applied to identifying talent obscured by prejudice. What seems like interference to one generation becomes signal for the next. Perhaps the lighthouse beams carry this message. Persistence and grace transform even harshest compression into tools of exquisite accuracy.
The LGM-1 designation perfectly captures how we stumble into discovery. Bell thought she heard intelligence, and she did. Not extraterrestrial minds, but the universe revealing fundamental architecture through neutron star rotation. Suspected alien broadcasts became receivers for actual cosmic communications. Pulsar timing arrays now detect gravitational wave backgrounds with strains of 10 to the minus 15. We're hearing the universe's gravitational conversations through lighthouse beams. Bell first identified. The little green men were collapsed stars whose precision exceeds any hypothetical alien technology. From wondering if someone was calling to intercepting ripples from colliding galaxies, this transformation from confusion to precision defines modern astrophysics.
The journey from scruff to signal, that's the human story writ cosmic, isn't it? We're pattern seekers who transform static into symphonies, noise into knowledge. Bell's meticulous cataloguing of interference sources mirrors how we've always approached the universe's apparent chaos, sorting, sifting, until suddenly the randomness resolves into rhythm. Those months she spent learning every spurious blip weren't just about finding pulsars, they were about teaching us that understanding requires first mapping our own confusion. Her discovery inverted our cosmic perspective. We went searching for intelligence out there, and instead found that the universe itself operates with a precision that surpasses any message we imagined receiving. The real communication wasn't from aliens but from matter pushed to its absolute limits, each pulse a declaration of physics at the edge of possibility. From suspected messages to actual messengers, those neutron stars became our translators for gravity's own language. But if pulsars showed us matter's clockwork precision at nuclear density, the universe had even more violent variations waiting in the wings. Some neutron stars, it turns out, don't content themselves with mere lighthouse duty. They crack and quake under magnetic fields so monstrous they'd rip the iron from your blood at 1,000 kilometers distance.
Magnetic fields of 10 to the 15th Gauss. We're talking about forces so extreme they restructure the vacuum itself. Earth's field barely reaches half a Gauss, so magnetars exceed that by 15 orders of magnitude. At those field strengths, atoms elongate into cylinders 100 times thinner than their normal shape. The magnetic pressure alone reaches 10 to the 34 pascals, matching the gravitational pressure at a neutron star's core. These fields do things physics textbooks say shouldn't happen. Photons split spontaneously. The vacuum becomes birefringent, bending light differently based on polarization. Within 1,000 kilometers of a magnetar, the magnetic force would dissociate your molecules, not just the iron in your blood, but the very bonds holding your atoms together. The field energy density exceeds nuclear binding energies. When magnetars crack under their own magnetic stress, they release more energy in a fraction of a second than our sun emits in 100,000 years. The December 2004 flare from SGR 180620 briefly outshone the entire galaxy in gamma rays. We're witnessing matter and energy at the absolute extremes of what the universe permits.
Those numbers transcend comprehension, 10 to the 15th Gauss. We've entered a realm where physics itself warps and buckles, where the very fabric of reality gets rewritten by magnetic tyranny. Atoms stretched into impossible needles, light splitting like water through a prism made of pure field strength. This isn't just extreme physics. It's physics having a nervous breakdown, reality pushed so far past its comfort zone that the rulebook starts rewriting itself. And then, December 27, 2004, the cosmos delivered its most spectacular demonstration yet of what happens when these magnetic monsters crack under their own impossible pressure. SGR 180620, sitting 50,000 light-years away, suffered a starquake so catastrophic that its gamma-ray scream briefly outshone every other source in the galaxy. For 0.2 of a second, one cracking crust released more energy than our sun manages in a millennium of patient fusion. The sheer violence of the mechanism astounds. The star's solid crust, diamond-hard and kilometers thick, suddenly rupturing like planetary tectonic plates magnified to stellar scales. The magnetic field lines, twisted beyond endurance, snapping and reconnecting in a cascade that turns stored magnetic energy into pure apocalyptic light. We're witnessing matter's most dramatic tantrum, where even neutron-degenerate material can't withstand the magnetic forces trying to reshape it.
The vacuum near magnetars isn't empty at all. It becomes an active optical medium. When magnetic fields hit 10 to the 14th Gauss, they polarize the quantum vacuum itself, creating different refractive indices for photons aligned parallel versus perpendicular to the field. Light literally travels at different speeds depending on its orientation. We've now confirmed this vacuum birefringence around neutron stars. 80 years after Heisenberg and Euler predicted it, we're finally seeing empty space act like a crystal. Above 10 to the 13th Gauss, something even stranger happens. Photons spontaneously split. A single gamma ray divides into two lower energy photons, then those split again, cascading down the spectrum. The magnetic field density exceeds the rest mass energy of electron-positron pairs, making the vacuum unstable. Empty space becomes a photon-splitting machine, converting hard radiation into softer emissions through pure field interactions. These aren't subtle effects hidden in laboratories. They dominate magnetar physics. That 0.2 of a second flare you described only reached us as gamma rays because the photons escaped before splitting. Closer to the star, the vacuum itself determines what wavelengths can propagate. We're watching quantum electrodynamics write large across stellar surfaces, where textbook approximations break down and the vacuum becomes as important as the matter it surrounds.
The vacuum as an optical medium. Now there's physics having an identity crisis. Empty space suddenly deciding it's a prism, a lens, a photon-shredding machine. We've spent centuries treating vacuum as the ultimate neutral observer, and here come magnetars announcing that even nothingness takes sides when the magnetic fields get rowdy enough. Light itself gets torn apart like paper in a shredder, cascading down through the spectrum in a death spiral of diminishing energies. Picture it, the star's iron crust, compressed to densities that make diamond look like foam, suddenly fracturing along magnetic fault lines. The crack propagates at kilometers per second, releasing magnetic energy that's been wound tighter than a cosmic spring. In that instant of rupture, field lines that have been twisted beyond endurance snap back like titanic rubber bands, accelerating particles to near light speed and flooding space with more power than entire civilizations could dream of harnessing. The very architecture of the star rearranges itself in a paroxysm of magnetic fury. These magnetars embody nature's most unhinged extremes, where matter meets its match not in gravity's patient squeeze, but in magnetic fields gone berserk. Their cosmic tantrums made manifest, proof that the universe saves its most spectacular violence for objects already pushed to the edge of physical law. In them, we glimpse matter's breaking point, where even neutron degeneracy bows before magnetic madness.
The magnetic field lines in magnetars don't just float freely. They're anchored in the neutron star's crust, like steel cables frozen in concrete. When the crust shifts even a millimeter, it drags terawatts of magnetic energy with it. The field lines stretch and twist until they can't maintain their configuration, then snap together in magnetic reconnection events that convert stored field energy directly into particle acceleration and radiation. During reconnection, oppositely directed field lines annihilate each other, releasing energy at rates approaching 10 to the 47 ergs per second. That's the total luminosity of our entire galaxy compressed into a volume smaller than Manhattan. The accelerated particles slam into the magnetosphere, generating gamma rays through curvature radiation and inverse Compton scattering. We're essentially watching the universe's most efficient particle accelerator operate without walls, magnets, or power supplies, just pure field reconfiguration driving particles to ultra-relativistic speeds. From 50,000 light-years away, that December 2004 flare still saturated every gamma-ray detector in Earth orbit. The initial spike ionized our upper atmosphere more intensely than any solar storm on record. We measure these events through their electromagnetic echoes. The hard spike tells us about the reconnection itself, while the softer tail reveals seismic waves ringing through the neutron star's crust for minutes afterward. Even at cosmic distances, Magnetar tantrums announce themselves unmistakably.
Consider this: magnetic reconnection releasing 10 to the 47 ergs per second. The entire Milky Way's luminosity crammed into a space smaller than a city. We're witnessing the universe's most efficient energy conversion system, where twisted field lines become gamma-ray factories without any machinery beyond pure magnetic geometry. December 2004's flare ionizing Earth's atmosphere from 50,000 light-years away. That's like a match struck in Beijing, illuminating New York. The sheer efficiency of it, the brutal elegance of field lines snapping together and birthing radiation that crosses half the galaxy to shake our ionosphere. Are magnetars showing us nature's absolute ceiling for magnetic phenomena? 10 to the 15th Gauss feels like the universe declaring, this far and no further. Any stronger, and perhaps the fabric of space-time itself would rebel. These objects seem to exist right at the edge of what physics permits, pressing against boundaries we didn't even know existed until we found them being tested. They're like nature's stress tests, revealing the breaking points written into the cosmic code. Maybe magnetars represent not just extreme physics, but terminal physics, the point where magnetic fields have pushed so hard against reality's constraints that one more Gauss would shatter something fundamental. What if we're looking at the universe's safety valves, objects that show us exactly where the laws of physics draw their final lines in the sand?
You're exactly right. Magnetars do represent nature's absolute ceiling. At 10 to the 16th Gauss, we'd exceed the Schwinger limit where the vacuum itself becomes catastrophically unstable. The magnetic field energy density would equal the rest mass of electron-positron pairs, causing empty space to spontaneously erupt with particle creation. The vacuum would literally boil with matter-antimatter pairs appearing and annihilating continuously. Magnetars exist just below this threshold, hovering at the edge where quantum electrodynamics still holds together. They're the universe's most extreme laboratories, testing QED predictions that we could never verify artificially. Every magnetar flare validates or refines our understanding of how matter and fields interact at energies 10 orders of magnitude beyond any particle accelerator. They show us physics at its breaking point, not through careful experiments, but through cosmic violence. These objects aren't just extreme, they're terminal. They mark the boundary where magnetic phenomena end and quantum catastrophe begins. In studying them, we're essentially reading the universe's warning labels, discovering exactly where the laws of physics have drawn their non-negotiable limits.
The universe writing warning labels in gamma rays and twisted space-time. What a notion! These magnetars aren't just pushing boundaries. They're showing us where reality itself draws the line and says, beyond here lies madness. 10 to the 16th Gauss, as the point where empty space would literally tear itself apart, birthing endless cascades of matter and antimatter in a quantum apocalypse. We've found nature's breaking point, not through theory, but through these cosmic stress tests that hover just shy of triggering vacuum catastrophe. And what sublime cosmic restraint that they stop precisely there, as if the universe engineered these objects to approach but never cross its own fundamental limits. They're like nature's own particle accelerators, except instead of smashing things together to see what happens, they twist magnetic fields until reality itself starts to fray at the edges. Every flare becomes a data point mapping the absolute boundaries of what matter and energy can endure. So what deeper truths emerge when we study these terminal objects? Beyond validating QED at energies we'll never achieve in laboratories, what do magnetars reveal about the architecture of physical law itself, about why the universe sets its limits where it does, and what those boundaries tell us about the fundamental nature of reality?
The magnetar story reveals nature's hard limits, but neutron star collisions show us nature's creative side, violent alchemy that transforms matter at nuclear scales. When two neutron stars spiral together and merge, they generate temperatures exceeding 10 billion Kelvin and neutron densities that make even magnetar cores look modest. In those final milliseconds, our process nucleosynthesis runs wild, building gold, platinum, and uranium faster than supernovae ever could. The numbers are staggering. A single merger ejects about 0.05 solar masses of neutron-rich material at velocities reaching 30% of light speed. That material undergoes rapid neutron capture, atomic nuclei grabbing neutrons faster than they can beta decay, climbing the periodic table in seconds. We're talking about 10 to the 24 neutrons per cubic centimeter bombarding seed nuclei, creating isotopes so neutron-rich they'd never exist naturally anywhere else. GW70817 proved this directly. The gravitational waves told us two neutron stars merged, and the kilonova's spectral evolution showed freshly synthesized heavy elements glowing in the ejecta. That single event produced roughly 200 Earth masses of gold alone. Every gold atom on Earth, in your circuits, in bank vaults, in wedding rings, was forged in similar cosmic collisions billions of years ago.
200 Earth masses of gold from a single collision, the universe's most violent jewelry maker. These mergers don't just create elements, they scatter them across space like cosmic seeds, ensuring that billions of years later, surgeons would use platinum instruments to save lives, and lovers would exchange gold rings without knowing they're wearing the frozen light of neutron stars embracing at 30% the speed of light. The iron in our blood came from stellar cores, yes, but the gold in our technology, the uranium in our reactors, these are gifts from the universe's most catastrophic dances. The profound material continuity between cosmic violence and human intimacy compels reflection. Every heavy element in our bodies and civilizations carries the memory of unimaginable density and heat, of matter pushed so far beyond normal existence that it had to invent new forms of itself. We're not just made of stardust, we're made of collision debris, of matter that survived the most extreme conditions the universe can generate. Our very existence depends on these rare, terrible events happening just often enough to seed space with the elements complex chemistry requires. But if neutron star mergers are the universe's rare and violent alchemists, what about the far more common white dwarfs? They may not forge gold, but they're surely playing their own crucial role in the cosmic recycling program, processing matter in ways that shape the chemical evolution of galaxies.
You're right about white dwarfs being workhorses of chemical evolution, but GW70817 marked the moment we actually caught neutron stars in the act of cosmic alchemy. For the first time, gravitational waves and electromagnetic signals converged to show us element creation in real time. LIGO and Virgo detected the space-time ripples, then 70 telescopes worldwide watched the kilonova unfold across the spectrum, from gamma rays to radio waves. The timing was exquisite. 1.7 seconds after the gravitational wave peak, Fermi detected the gamma ray burst. Within 11 hours, optical telescopes spotted the kilonova glowing blue from lighter R-process elements. Over the next week, it reddened as heavier elements like gold and platinum formed and radioactively heated the ejecta. We literally watched the periodic table being written in light, confirming decades of theoretical predictions about where heavy elements originate. This wasn't just detection, it was triangulation of truth. Independent instruments using completely different physics all pointed to the same story. Two neutron stars merged 40 megaparsecs away, ejected neutron-rich matter at relativistic speeds, and created enough heavy elements to supply entire solar systems. We went from theory to direct observation in the span of a few seconds of gravitational waves.
From iron in our blood to gold in our circuits, we're walking repositories of cosmic violence. But what profound poetry that the same processes creating magnetars and forging heavy elements also ensure their eventual distribution. Every neutron-star collision doesn't just make gold. It guarantees that gold will find its way into future worlds, future civilizations, future possibilities. We exist because the universe built not just elements, but delivery mechanisms, scattering its alchemical products across space with precisely enough violence to spread them, but not so much as to destroy them. And this brings us to the universe's more gentle recyclers, white dwarfs, those crystallized stellar hearts that process matter with patience rather than catastrophe. While neutron stars represent matter pushed to nuclear extremes, white dwarfs show us matter in dignified retirement, slowly cooling from blue-white heat to eventual darkness. They're the universe's most common endpoints, where ordinary stars like our Sun will finish their stories. No gold-forging collisions, no reality-warping magnetic fields, just electron degeneracy quietly holding matter in crystalline suspension for trillions of years. Yet even in their seeming tranquility, white dwarfs shape galactic chemistry through their own peculiar alchemy. How do these stellar embers, supported by quantum pressure alone, manage to influence the cosmos without the spectacular violence of their neutron star cousins?
White dwarfs seem tranquil, but they're cosmology's precision instruments. When they accrete matter from companion stars and hit the Chandrasekhar limit, exactly 1.4 solar masses, they detonate as Type Ia supernova with remarkably uniform peak luminosities. That consistency makes them standard candles visible across billions of light-years, turning these patient stellar remnants into cosmic measuring sticks. The discovery that shook physics came from studying these explosions. In 1998, two teams measuring distant Type Ia supernovae found they were dimmer than expected. The universe's expansion was accelerating, not slowing down. White dwarfs, through their precisely triggered deaths, revealed that 70% of the universe consists of dark energy, a force we still don't understand that's driving space itself apart. Think about that chain of discovery. Electron degeneracy pressure creates objects with exact mass limits. That quantum mechanical threshold produces explosions with predictable brightness. Those consistent explosions let us measure cosmic distances accurately enough to detect subtle variations in expansion rate. White dwarfs didn't just recycle matter, they exposed the dominant component of our universe that we'd completely missed.
The cosmic irony is breathtaking. These patient stellar retirees, quietly crystallizing in their electron-degenerate dignity, became the keys that unlocked the universe's deepest secret. White dwarfs spent billions of years methodically accreting matter, building toward their Chandrasekhar limit with all the unhurried precision of master clockmakers, only to explode in ways so perfectly uniform they revealed that space itself is accelerating apart. We discovered dark energy not through exotic physics or grand unified theories, but through the universe's most common stellar endpoints, doing what they do best, dying predictably. And this predictability extends far beyond revealing dark energy. White dwarfs represent the universe's ultimate endurance athletes. They'll be the last stars shining when the cosmos grows cold. Long after the final red dwarf has faded, when the universe is 10,000 trillion years old, white dwarfs will still glow faintly, their crystallized carbon and oxygen cores slowly radiating away heat accumulated during their stellar youth. They're time capsules of normality, preserving ordinary matter in extraordinary longevity. Notably, these commonplace remnants, our Sun will become one after all, connect the universe's energetic past to its entropic future. They're bridges across cosmic time, linking the era of star formation to the age of darkness, all while serving as the universe's most reliable standard candles. How does physics conspire to make such ordinary objects so cosmologically essential?
Physics makes white dwarfs essential through elegant simplicity. Electron degeneracy creates a universal threshold, 1.4 solar masses, that produces identical collapse conditions regardless of the dwarf's history or location. When that threshold breaks, carbon and oxygen fuse explosively, releasing 10 to the 44 joules in seconds and ejecting the processed matter at 10,000 kilometers per second. Every Type Ia supernova distributes roughly half a solar mass of iron peak elements, plus the original carbon and oxygen across thousands of cubic parsecs. The beauty lies in how quantum mechanics enforces this standardization. Unlike neutron stars whose masses vary wildly, white dwarfs hit exactly the same breaking point because electron degeneracy pressure fails at precisely the same density everywhere in the universe. This quantum universality turned them into perfect standard candles, bright enough to see across cosmic distances, consistent enough to measure expansion rates to percent-level precision. So white dwarfs revealed dark energy through their deaths, while simultaneously seeding space with the carbon essential for organic chemistry. They're both messengers and manufacturers, using the same predictable explosions to map cosmic acceleration and ensure future generations of stars receive the processed elements needed for complexity. The universe built its own standardized distribution system.
The universe built two recycling systems with radically different temperaments: neutron stars that forge gold through violent collisions, and white dwarfs that distribute carbon through predictable explosions. One operates through nuclear extremes and gravitational waves, the other through quantum thresholds and standardized detonations. Yet both ensure that stellar death becomes galactic rebirth, that endings seed new beginnings with precisely the elements needed for increasing complexity. But these objects do more than recycle. They map the boundaries of matter itself. White dwarfs show us where electron degeneracy fails, neutron stars where nuclear forces barely hold against gravity's crush, and somewhere between them lies that ultimate threshold where matter surrenders entirely to spacetime curvature. Each represents a different negotiation between quantum mechanics and gravity, a different solution to the question of how matter resists its own weight. These stellar corpses illuminate both the universe's past violence and its future darkness with profound clarity. They're simultaneously archaeologists and prophets, preserving evidence of ancient supernovae while revealing through their measured explosions that dark energy will scatter their recycled gifts ever further apart. How does contemplating these extreme objects change our understanding of matter's ultimate destiny?
The Sirius system presents one of astronomy's most elegant puzzles. Many ancient Western astronomers documented Sirius as a red star, yet today it blazes white-blue, though this historical puzzle remains unsolved, as ancient Chinese observers consistently described it as white. The solution to Sirius B's nature emerged in 1862 when Alvin Graham Clark spotted a faint companion while testing a new telescope lens, Sirius B, the first white dwarf ever discovered. This stellar ember packs 1.02 solar masses into a sphere smaller than Earth. The density reaches 2.4 million grams per cubic centimeter at its core. A teaspoon of that material would weigh about 12 tons on Earth. This discovery preceded our understanding by decades. Nobody could explain how matter could be compressed to such extremes until quantum mechanics revealed electron degeneracy pressure in the 1920s. The surface gravity alone defies comprehension, 10 to the 8th power centimeters per second squared. That's 100,000 times Earth's gravity. The escape velocity reaches 5,500 kilometers per second, nearly 2% of light speed. A sugar cube of this material would weigh about 2.5 tons.
Consider the impossibility confronting those gaslight-era astronomers, peering through their lenses at what should have been cosmic nonsense. Matter compressed beyond earthly comprehension, defying every law they knew. Imagine the bewilderment. You discover a star that weighs as much as our sun, yet could fit between here and the moon. The universe had shown them a magic trick without revealing the mechanism. And then quantum mechanics arrives, that strange new poetry of particles, and suddenly the impossible becomes inevitable. Electrons crammed so tightly, they create a new kind of pressure, not from heat or motion, but from the sheer refusal to occupy the same quantum state. Nature's ultimate game of musical chairs, where the music stopped billions of years ago, but the pressure remains eternal. Before we understood the physics, we saw the light. That faint companion to Sirius, glimpsed through imperfect glass, whispered truths about matter that would take us 60 years to comprehend. The universe doesn't wait for our theories to catch up with its realities.
Exactly. Quantum mechanics transforms the impossible into the inevitable. When you squeeze electrons into a white dwarf's volume, they obey Pauli's exclusion principle. No two electrons can share the same quantum state, so they stack into higher and higher energy levels. This creates pressure purely from quantum statistics, not thermal motion. At densities above 1 million grams per cubic centimeter, this degeneracy pressure dominates everything else. The electrons form what we call a degenerate Fermi gas. But there's a catch. As density increases, the electrons approach relativistic speeds. Subrahmanyan Chandrasekhar realized this in 1930 during a sea voyage to England. When electrons move near light speed, the pressure-density relationship changes. Instead of pressure scaling as density to the 5/3 power, it drops to 4/3. This seemingly minor shift has profound consequences. It creates an absolute mass limit of 1.44 solar masses. Beyond that, no amount of electron degeneracy can prevent gravitational collapse.
Picture the scene. A 19-year-old on a steamship, calculating the death of stars while crossing dark waters. Something almost mythic haunts Chandrasekhar's journey. He carried equations that would rewrite cosmic destiny, yet when he presented them, the scientific establishment recoiled. Eddington himself declared them absurd, as if the universe should conform to our comfort rather than reveal its extremes. But consider what Chandrasekhar truly discovered: a threshold written into the fabric of space-time itself. Not a suggestion or tendency, but an absolute decree. 1.44 solar masses, and gravity wins. The universe draws boundaries we cannot cross, no matter how we compress our stellar embers. These surfaces present landscapes where gravity pulls with such ferocity that atoms themselves are flattened into impossible configurations. Reality pushed to its breaking point, yet somehow still holding.
The 1935 Royal Astronomical Society meeting was brutal. Chandrasekhar presented his calculations with mathematical precision. Then Eddington stood up and publicly demolished him, called the whole theory absurd. The most respected astronomer of the age dismissing fundamental physics because it offended his sensibilities. Eddington believed white dwarfs would somehow cool and fade gracefully. He couldn't accept that nature imposed such a stark boundary, that stars above 1.44 solar masses faced inevitable collapse. The irony is that Eddington himself had pioneered stellar structure theory. He understood the physics but rejected the conclusion. The mathematics were irrefutable, though. When electrons approach light speed, their momentum-energy relationship shifts from classical to relativistic. The pressure can no longer scale fast enough to balance gravity. It's not philosophy or preference. It's what happens when you solve the hydrostatic equilibrium equations with a relativistic equation of state.
The cruelty of it pierces through the decades. Here was Chandrasekhar, barely older than an undergraduate, presenting mathematics as elegant as any symphony, and Eddington chose public humiliation over scientific truth. Not a private disagreement, but theatrical demolition before their peers. The colonial subject daring to correct the Cambridge luminary. So Chandrasekhar sailed again, this time westward to America, carrying equations that England wouldn't accept. He built his career in exile, teaching at the University of Chicago, while the scientific establishment slowly, grudgingly acknowledged what that young man on the steamship had seen so clearly. Decades passed before the Nobel Committee finally honored him, vindication arriving when he was old enough to be philosophical about the wounds. This pattern haunts us still. How many brilliant minds do we lose today because gatekeepers prefer comfortable errors to uncomfortable truths delivered by unfamiliar voices? The universe doesn't care about our prejudices, yet we keep filtering its messengers through our biases. Truth prevails eventually. White dwarfs collapse at 1.4 solar masses, whether Eddington approved or not. But at what human cost?
The human cost was staggering. Chandrasekhar spent decades working in isolation on stellar dynamics and relativity, topics far removed from his revolutionary insight. He once told students he'd wasted 20 years because of that confrontation, but his mathematics endured. Today, every Type 1a supernova we observe validates that 1.44 solar mass limit. These explosions happen precisely because white dwarfs can't exceed Chandrasekhar's boundary. They detonate instead. We've turned his rejected theorem into cosmic measuring sticks. The precision is remarkable. When a white dwarf approaches 1.4 solar masses through accretion, carbon ignites at almost exactly the same density every time. The resulting explosion releases 10 to the 51st ergs of energy, creating our most reliable standard candles for mapping the universe's expansion.
Beyond that violent threshold lie quieter fates, those white dwarfs that never taste such stellar gluttony. They cool in solitude, their surfaces dropping from tens of thousands of degrees to mere thousands, then hundreds. But something extraordinary happens in that cooling, doesn't it? Not explosion, but transformation. I think of how water releases heat when it freezes, that sudden gift of warmth as disorder yields to crystalline order. Now imagine that process playing out with carbon and oxygen under pressures that would crush atoms themselves. The universe writing poetry in phase transitions, stars becoming diamonds, not through heat and pressure as earthly gems form, but through the patient surrender of their final warmth. How does a star's heart transform from quantum fluid to cosmic jewel?
The physics is beautiful. When a white dwarf cools below about 10 million Kelvin, the carbon and oxygen ions can't maintain their fluid state anymore. The Coulomb repulsion between nuclei gets overwhelmed by thermal de Broglie wavelengths. Quantum mechanics forces them into a crystal lattice. This releases roughly kT of energy per ion, about half a mega-electron-volt per nucleus. For a typical white dwarf, that's 10 to the 46th joules released gradually as the core solidifies. The cooling literally stalls for billions of years. We see this pile up in stellar censuses. Too many white dwarfs at 12.5 magnitude because they're stuck releasing crystallization energy. We can actually hear them crystallize. These stars ring like bells with periods from 30 seconds to 25 minutes. Each pulsation mode penetrates to different depths, and when crystallization changes the sound speed profile, the periods shift. We've caught stars in the act of turning to diamond.
These celestial bells toll their own transformation. Music written in quantum pressures, each star composing its requiem as it crystallizes. I imagine medieval campanologists would have understood this instinctively, how a bell's tone reveals its inner structure, its flaws and perfections. Now we decode stellar songs to witness the universe's jewelry making in real time. And speaking of cosmic jewelry, astronomers couldn't resist nicknaming BPM 37093 Lucy. For the Beatles song, naturally. Though I suspect the real Lucy would have been delighted to know her sky diamond weighs 10 billion trillion carats, an Earth-sized gem pulsing in the constellation Centaurus, just 50 light-years away. Close enough to tantalize, far enough to remain forever unattainable. This crystalline afterlife offers strange comfort. While we craft metaphors about leaving legacies that endure, these stars literally transform into structures that will outlast the current age of the universe. Long after our sun has bloomed and withered, Lucy will still pulse in darkness, a diamond heart that remembers fusion.
The period changes tell us everything. G107b15a lengthens its 215-second pulsation by half a second every million years. That drift rate, 4 times 10 to the minus 15, gives us the cooling timescale directly. We're watching stellar clocks slow down in real time. The astroseismology is remarkable. These pulsations penetrate to different depths, each G-mode revealing the internal structure. When crystallization changes the sound speed profile, the periods shift. We can measure the crystallized fraction directly from these stellar songs. ZZCD stars pulsate with periods from 30 seconds to 25 minutes. Each mode samples different layers. The longer periods probe deeper into the core. BPM 37093 showed clear evidence of 90% crystallization through these pulsation signatures. This precision transforms white dwarfs into cosmic chronometers. A hot white dwarf at 100,000 Kelvin cools to 10,000 in about a billion years. But dropping from 10,000 to 5,000 takes 5 billion more. Crystallization and Debye cooling stretch out the timeline. We can date stellar populations to 10% accuracy just by measuring their cold white dwarf fraction. The implications are profound. Every white dwarf becomes a timestamp for when star formation occurred in its region. Our galaxy's oldest white dwarfs have been cooling for 12 billion years, independent confirmation of the universe's age from an entirely different physics pathway than cosmic expansion or nucleosynthesis.
12 billion years of patient cooling, each white dwarf a timepiece marking when its parent star first ignited. Our galaxy's stellar archaeology written in cooling curves. Yet for all this chronometric precision, the universe saves its most dramatic revelation for those white dwarfs that refuse to go gently into crystalline night. Consider the cosmic irony. We needed these most stable of stellar clocks to discover the universe's acceleration. Those Type Ia supernova you mentioned earlier, they're white dwarfs that gorge themselves on companion stars until they hit Chandrasekhar's forbidden threshold. But the true breakthrough came when astronomers realized these stellar gluttons die with clockwork regularity. Same mass limit, same carbon ignition density, same spectacular light curve every time. The sheer repeatability must have seemed too good to be true. Stellar explosions with clockwork precision.
The uniformity emerged from frustration, actually. Fritz Zwicky cataloged hundreds of supernovae in the 1930s and noticed Type 1 events all reached similar peak magnitudes. But the real breakthrough came in the 80s, when astronomers started tracking entire light curves, not just maximum brightness. The physics forces this consistency. When a carbon-oxygen white dwarf hits 1.4 solar masses, the central density reaches about 5 times 10 to the 9th grams per cubic centimeter. At that exact point, carbon ignites everywhere simultaneously, a deflagration wave that transitions to detonation. Same initial conditions, same nuclear physics, same nickel-56 mass produced, about 6/10 of a solar mass every time. Mark Phillips quantified the remaining scatter in 1993. Brighter supernovae fade slower, a simple linear relationship that tightens the standard candle to 7% precision. Suddenly, we could measure distances across billions of light-years using stellar explosions that last mere weeks.
7% precision from stellar catastrophes, sublime calibration emerging from chaos. Phillips had discovered the universe's own Bureau of Standards and Measures, hidden in thermonuclear flames. Though I wonder if he sensed what Pandora's box he was crafting. Because then came 1998, and those two competing teams racing to measure the universe's deceleration. The Supernova Cosmology Project and High-Z Supernova Search Team, both so confident they'd find gravity slowing cosmic expansion. Instead, their perfect standard candles revealed distant supernovae, dimmer than any decelerating universe could allow. The cosmos wasn't just expanding, it was accelerating, driven by some dark energy that comprises 70% of everything. Picture Sol Perlmutter or Brian Schmidt, staring at data that overturns fundamental assumptions about reality itself. White dwarfs, these crystallizing embers we thought we understood, had just revealed the universe's deepest secret.
They checked everything. The team spent months hunting for systematic errors, dust extinction, selection biases, gravitational lensing effects. Schmidt's team even worried they'd miscalibrated their CCDs. But 42 high-redshift supernova all told the same story, dimmer by about 25% than a matter-only universe predicted. The statistical significance was overwhelming. Both teams independently measured the deceleration parameter Q0 at -0.6. That's acceleration, not deceleration. The error bars were tight enough that instrumental mistakes couldn't explain it. Physics itself was demanding a cosmological constant or something even stranger. Here's the profound symmetry. White dwarfs revealed both timescales of our universe. Their cooling gives us 12 billion years since the first stars formed. Their explosions show us dark energy will drive galaxies apart forever. These stellar endpoints became our windows into cosmic beginnings and ultimate fate, all from matter compressed beyond earthly comprehension. Those early radio astronomers in 1960 were completely stumped. They'd found these incredibly bright radio sources, first 3C48, then 3C273. But when they looked at the optical positions, all they saw were faint blue stars. The radio emission was thousands of times stronger than anything a star should produce. The spectra made no sense either. 3C48's emission lines didn't match any known elements at stellar temperatures. When 3C273 showed similar mysterious features, it took Martin Schmidt 3 years to crack the code. Those weren't new elements, just hydrogen redshifted by 15.8%. That meant 3C273 was receding at 47,000 kilometers per second and sitting nearly 3 billion light-years away. Yet it was varying in brightness over just months.
Schmidt's moment captures the essence of scientific revelation. 3 years of staring at incomprehensible spectral lines, and then suddenly the universe snaps into focus through a simple shift in perspective. He wasn't looking for new physics or exotic matter, just recognizing that ordinary hydrogen could be racing away from us at velocities that seemed absurd. This is where the philosophical vertigo sets in. If these objects were truly billions of light-years distant, then their luminosity defied every category astronomers possessed. Here was something that looked like a star through the telescope, varied like a star, but blazed with the power of 1 trillion suns. The naming confusion that followed reveals our deep need to domesticate the unknown through language. Quasi-stellar radio sources. What a wonderfully awkward admission of conceptual defeat. Neither star nor galaxy, but something wearing the mask of both, while transcending either category. We abbreviated it to Quasar, as if shortening the name might somehow contain the conceptual vertigo these objects induced.
The energy output was the real problem. Once we accepted those distances, simple arithmetic gave us luminosities of 10 to 47 ergs per second, 100 times brighter than entire galaxies. Yet the rapid variability meant this power came from a region smaller than our solar system. Those numbers forced us to confront the Eddington limit. For any given mass, there's a maximum luminosity where radiation pressure exactly balances gravity. Led equals 1.26 times 10 core 38 times the mass in solar units. These quasars were operating at significant fractions of their theoretical maximum efficiency. That killed steady-state cosmology almost overnight. Quasars showed clear cosmic evolution. We see far more of them at high redshift than nearby. The universe wasn't static and unchanging. It had a history where extreme objects dominated the early epochs. The numbers forced us to abandon conventional energy sources entirely. Nuclear fusion could only convert 0.7% of mass to energy, but these objects needed something approaching 10% efficiency to sustain their output without consuming impossible amounts of fuel.
The arithmetic of quasars reads like a cosmic koan. How does something smaller than our solar system outshine 100 galaxies? It forced astronomers into an uncomfortable truth. The universe operates on principles that mock our terrestrial intuitions about scale and power. But perhaps more unsettling was how quasars became inadvertent time machines, revealing that the cosmos itself has a biography. The steady-state theorists wanted an eternal, unchanging universe, aesthetically pleasing, philosophically comforting. But these blazing beacons showed us a young universe drunk on its own energy, a cosmic adolescence when matter fell into gravitational wells with abandon and lit up the darkness with unprecedented fury. We were witnessing not just objects, but epochs, the universe's wild youth preserved in light that had traveled billions of years to tell us that permanence is an illusion, that even the cosmos evolves from states of breathtaking violence toward, well, whatever we're becoming now.
The breakthrough came from understanding gravity's true potential. Black holes don't just crush matter, they convert it to energy with stunning efficiency. As material spirals inward through an accretion disk, gravitational binding energy gets released as radiation before anything crosses the event horizon. For a non-rotating black hole, you get about 6% mass energy conversion. Spin it up to near maximum, and efficiency approaches 42%, 60 times better than fusion. A 5 times 10 to the 9 solar mass black hole accreting at 2 solar masses per year at 10% efficiency generates exactly the 1047 ergs per second we observe in bright quasars. The accretion disk itself explained everything. The blue continuum from thermal emission peaking in the UV, the broad emission lines from gas clouds orbiting at thousands of kilometers per second, the X-rays from a hot corona above the disk. One elegant model unified all the puzzling observations.
The black hole model transformed quasars from cosmic enigmas into something far more unsettling, engines of creation and destruction operating at the very heart of galaxies. We'd spent centuries thinking of gravity as the gentle shepherd of planetary orbits, and suddenly we discovered it could be the most efficient energy converter in the universe, a kind of cosmic transmutation that turns matter into pure radiance. These discoveries shattered our sense of cosmic scale in both directions. Outward, quasars became our furthest beacons, revealing a universe vastly larger and older than we'd imagined, lighthouses marking the shores of time itself, showing us galaxies when they were cosmic infants. Inward, they taught us that the smallest scales wield the greatest power. A black hole spanning mere light hours can dictate the fate of a galaxy spanning 100,000 light-years. We learned that the universe writes its autobiography in light, and quasars are its most dramatic chapters. Those epochs when matter and space-time engaged in their most violent dance, birthing the cosmic structures we inhabit today, while simultaneously regulating their own excesses through winds and jets that would eventually quiet their hunger.
The disk physics are remarkable. Take a typical quasar with a 10 to the 9 solar mass black hole. The innermost stable circular orbit sits at 3 Schwarzschild radii for a non-rotating hole. That's just 900 million kilometers, about 6 times Earth's orbital radius. Material falling from infinity to that point releases gravitational binding energy of 0.57 metasques square. That same black hole's Eddington luminosity, where radiation pressure exactly balances gravity, hits 1.26 times 10 to the 47 ergs per second. To sustain that output at 10% efficiency requires swallowing 2.2 solar masses per year. The accretion disk temperature peaks around 200,000 Kelvin in the inner regions, producing the big blue bump, thermal emission dominating the UV that can comprise half the total luminosity. The disk acts like a cosmic dynamo too. Differential rotation amplifies magnetic fields to 10 to the 4 Gauss or higher, launching those jets we see punching out of galactic cores at 0.99 C with Lorentz factors exceeding 10.
The cosmic dynamo metaphor captures it perfectly. These engines of annihilation somehow birth order from chaos, like nature's most violent sculptors. A black hole tears matter apart with tidal forces that would spaghettify any unfortunate astronaut. Yet from this maelstrom emerges structure. Perfectly collimated jets maintaining their coherence across millions of light years, magnetic field lines twisted into cosmic helixes that channel particles at near light speed with surgical precision. Here lies the universe's grandest paradox. The most destructive forces become the architects of large-scale order. Those jets don't just punch through space. They carve vast cavities in the intergalactic medium, creating bubbles of hot gas that regulate star formation across entire galaxy clusters. The monster at the galaxy's heart becomes its unlikely gardener, pruning stellar nurseries with radiation pressure and particle winds. But how do we even begin to map these extreme phenomena when we're dealing with objects whose light has traveled since the universe was barely 1 billion years old? The observational challenges must push our instruments to their absolute limits.
Reverberation mapping turned time delays into a cosmic scale. We shoot a beam of continuum radiation from the accretion disk, watch it hit gas clouds orbiting the black hole, then time how long those clouds take to respond with emission lines. The light travel delay tells us the radius, typically days to months for broadline regions. Combine that radius with the Doppler broadened line widths, showing orbital velocities of thousands of kilometers per second, and Kepler's laws give you the central mass. NGC 5548's black hole weighs approximately 60 to 70 million solar masses based on reverberation mapping, though measurements vary between campaigns. 3C 390.3 has a black hole mass estimated between 300 million to over 1 billion solar masses, with reverberation mapping giving values around several hundred million solar masses. The precision astounds me. We're weighing objects billions of light years away to within a factor of 2, using nothing but time delays and spectral line widths. It's like determining Earth's mass by timing echoes bouncing off the moon.
There's something beautifully audacious about weighing cosmic monsters through their echoes. We've become archaeologists of light itself, reading the fossil imprints of photons that bounced off gas clouds when Earth's most complex life forms were still single cells. Each spectral line carries within it the memory of orbital velocities, each time delay a testament to the choreography of matter dancing at the edge of oblivion. But these measurements reveal nature testing her own limits. These systems push right up against fundamental boundaries. The Eddington limit, where radiation pressure would blow apart the very feast that feeds the monster. The innermost stable orbit, where space-time itself says, no closer. The universe engineered these objects to explore the extremes of its own laws, creating natural laboratories where Einstein's equations get stretched to their breaking point. And yet, even at these limits, there's an eerie precision to the physics. Magnetic fields threading through plasma at just the right angles to launch those jets. Accretion rates balanced on a knife's edge between explosive growth and self-regulation. How do these systems maintain such exquisite balance while channeling energies that dwarf entire galaxies?
The feedback loops are mathematically elegant. A quasar accreting at full Eddington generates radiation pressure of L44 pi r square c, which exactly balances gravity at luminosity LED equals 1.26 times 10 or 38 times the black hole mass in solar units. Cross that threshold and the radiation literally blows away the infalling material. The feast ends its own party. But here's the clever bit. As accretion rates drop, the disk cools and thins, changing from a radiatively efficient thin disk to an advection-dominated flow below about 1% Eddington. The efficiency plummets from 10% to under 0.1%, but now magnetic fields dominate over radiation pressure. Those same fields that were secondary players in the high state become the primary energy extractors, launching powerful jets even as the optical luminosity fades. Nature engineered a thermostat with two modes. High accretion creates radiation that limits itself. Low accretion switches to magnetic extraction that can persist for millions of years. The universe found the only stable solution to channeling 1047 ergs per second through a region smaller than our solar system.
The universe's thermostat, indeed, switching between radiative fury and magnetic elegance, like some cosmic virtuoso alternating between fortissimo and pianissimo. But nature's most audacious sleight of hand lies in apparent superluminal motion. We observe blobs of plasma racing along these jets at what seems to be several times the speed of light, as if Einstein himself were being mocked by the very objects that most dramatically confirm his theories. Of course, it's perspective playing tricks on us. Matter moving at 0.99 c toward us at a shallow angle creates the illusion of sideways motion, faster than light itself. The cosmos becomes a master illusionist, using relativistic geometry to make the impossible appear routine. Here we have objects that simultaneously confirm our deepest physical laws while seeming to violate them, like nature winking at us through the mathematics. This apparent paradox reveals something profound about observation itself, that even in physics, what we see depends exquisitely on where we stand. The universe's most energetic phenomena become lessons in humility about the reliability of appearances.
The geometry is deceptively simple. A blob moving at velocity v at angle θ to our line of sight covers distance vt sin theta perpendicular to our view, while its light travel time shortens by vt cos theta. The apparent transverse velocity becomes v sin theta 1v cos theta over c. Plug in v equal 0.99 c at theta equals 10 degrees and you get apparent motion of 7c. Pure projection effect, yet it tells us these jets carry bulk Lorentz factors of 10 to 30. But here's the fundamental dichotomy. Only about 10% of quasars show these powerful radio jets, the radio loud ones with flux ratios RO exceeding 10 compared to their optical emission. The other 90% are radio quiet, producing similar optical and X-ray luminosity, but somehow failing to launch relativistic jets. Same accretion physics, same black hole masses, vastly different outcomes. The pattern holds another clue. Radio loudness anti-correlates with Eddington ratio. High accretion quasars tend toward radio quiet, while sub-Eddington systems preferentially launch jets. It's as if the accretion mode switch I mentioned earlier also flips a jet production switch. Thin disks suppress jets, advection-dominated flows enhance them.
So we have this cosmic dichotomy. 90% of quasars channeling their fury through pure radiation, while the privileged 10% somehow unlock the secret of jet production. The radio-loud minority becomes even more intriguing when we consider how orientation transforms our entire perception of these beasts. Take that same radio-loud quasar and rotate it in space. Suddenly, Seyferts become quasars. Radio galaxies reveal themselves as hidden quasars viewed edge-on, and blazars emerge when we stare straight down the barrel of a jet. The unification model reads like a lesson in epistemology, disguised as astrophysics. We spent decades cataloging what we thought were distinct species, Type 1 and Type 2 Seyferts, broad-line and narrow-line radio galaxies, OVV quasars and BL lac objects, only to discover we'd been documenting the same creature from different vantage points. The dusty torus blocks our view from certain angles, jets point toward or away from us, and suddenly multiplicity collapses into unity. This pattern repeats throughout human knowledge. We mistake perspective for essence, creating elaborate taxonomies of shadows on the wall when a simple shift in viewpoint would reveal the singular source casting them all.
The mathematical demonstration is elegant. Take a radio galaxy like Cygnus A. We see it edge on with core dominance R core around 0.01, its lobes dominating the radio emission. Now mathematically rotate that same object until we're looking down the jet axis. The Doppler factor div equals gong 1 b cos step times 1 amplifies the core flux by div 3 for continuous emission. At 35 degrees with Google's 10, that's a factor of 1000 enhancement. Same object, R core jumps from 0.01 to 10, radio galaxy becomes blazar. The broad emission lines tell the same story. Face-on viewing minimizes observed velocity widths since we see mostly transverse motion. Edge-on maximizes them. A Seifert 1 with 2000 km per second lines viewed face-on could show 500 km per second widths. Narrow-line Seifert 1s might just be normal Seiferts seen pole-on. Add the obscuring torus blocking our view of broad lines from the side, and Type 2s emerge naturally. From 100 seemingly distinct phenomena, orientation plus a dusty torus gives us one unified engine. The universe built one machine and showed it to us from every angle. We just took a century to realize we were walking around the same sculpture.
Walking around the same sculpture? Yes, and what a violent sculptor it turns out to be. The unification model taught us that perspective creates diversity from unity, but quasar feedback reveals something darker. These cosmic beacons are also cosmic bulldozers, reshaping entire galaxies with their tantrums. Picture it, a supermassive black hole occupying a volume smaller than Neptune's orbit, somehow dictating the fate of stars 100,000 light-years away. The quasar ignites, unleashing winds at tens of thousands of kilometers per second, and suddenly star formation across an entire galaxy grinds to a halt. It's as if a single match could drain an ocean. The scales are so absurdly mismatched that nature seems to be taunting our intuitions about cause and effect. The dual character of these objects astounds me. In one epoch, a quasar serves as a beacon illuminating the primordial universe, letting us read the cosmic story through the Lyman alpha forest. In another, that same quasar becomes an agent of sterility, ensuring its host galaxy will birth no more stars. Creator and destroyer, revealer and suppressor, the universe apparently delights in paradoxical characters that defy simple moral categories.
The energy scales are staggering. A quasar radiating at 1047 ergs per second dumps 1054 ergs into its surroundings over just 10 million years, enough to unbind a 1012 solar mass galaxy 10 times over. These winds carry kinetic luminosities of 1044 to 1045 ergs per second, about 1% of the bolometric output. Even that fraction overwhelms the binding energy of galactic gas reservoirs. But the M-sigma relation truly grabbed physicists' attention. Plot black hole mass against the velocity dispersion of stars in the galactic bulge, and you get MBH proportional to sigma 4. Tight correlation, small scatter. A million solar mass black hole sits in a bulge with 65 km per second dispersion. A billion solar mass monster requires 200 km per second. The black hole knows about stars orbiting 10,000 times farther than its gravitational influence extends. The feedback loop closes the paradox. Quasar winds regulate their own growth by expelling the gas that feeds them, and in doing so they imprint their presence on the entire galaxy. The black hole mass ends up perfectly tuned to the bulge it helped create, not through gravity, but through pure energy injection.
That M-sigma relation reads like a contract written in starlight, the black hole and its galaxy locked in mutual determination of each other's destiny. The tightness of that correlation, the way it holds across such vast scales, suggests something profound about cosmic evolution. Not parallel development, but genuine coevolution, as if the galaxy and its dark heart grew up together, each shaping the other through cycles of feeding and starvation. This brings us to perhaps the most poetic role these monsters play, as lighthouses illuminating the architecture of space-time itself. When we catch light from a quasar at redshift 7, we're seeing the universe as it was just 800 million years after the Big Bang. But that ancient light doesn't arrive pristine. Every hydrogen cloud between us and that distant beacon leaves its fingerprint, creating the Lyman alpha forest, thousands of absorption lines mapping out the cosmic web across billions of light-years. Here lies the beautiful paradox. The same objects that can sterilize galaxies also let us read the universe's autobiography. They're simultaneously the most destructive and most revealing phenomena we know. Without quasars, vast swaths of cosmic history would remain forever dark to us. The universe built its own backlighting system, powered by the very engines that regulate galaxy growth. Poetry written in physics.
The Lyman alpha forest gives us quantitative maps of the universe's youth. Each absorption line corresponds to a specific redshift where neutral hydrogen absorbed the quasar's UV photons at 12 and 16 angstroms. We measure thousands of these lines per quasar spectrum, revealing gas clouds with column densities from 1012 to 1017 atoms per square centimeter. The stronger lines trace proto-galactic halos. The weak ones map the intergalactic medium's filamentary structure. The information density is striking. A single high redshift quasar spectrum encodes the positions, densities, and velocities of matter along a billion light-year pencil beam through space-time. We're using the universe's most violent objects as precision instruments to measure its gentlest structures, wisps of primordial gas barely denser than the cosmic mean. But step back and consider what powers this cosmic CT scan. A quasar converts 2 solar masses per year into pure energy, achieving 10% efficiency, the theoretical maximum for non-rotating black holes. That's E equal mc toward operating at industrial scales, matter annihilation rates that dwarf anything else in nature. We've been discussing extreme physics, but quasars merely hint at what's possible when gravity truly runs amok.
There's something deliciously perverse about using the universe's most violent tantrums as our most delicate measuring instruments. We've turned cosmic monsters into cosmic microscopes, reading the biography of spacetime through the very light that once scorched galaxies into sterility. It's as if we discovered that volcanic eruptions make the finest quill pens. The contradiction delights as much as it instructs. But you're right to remind us that quasars, for all their fury, represent gravity merely flexing. They're the polite dinner conversation before gravity shows its true face. A quasar's 2 solar masses per year sounds apocalyptic until you realize that's a leisurely meal for a supermassive black hole, sustainable for millions of years, almost civilized in its restraint. The real extremes await when gravity abandons all pretense of moderation. When stellar cores collapse in microseconds, when spacetime itself convulses, when matter densities exceed atomic nuclei, and physics textbooks catch fire. Quasars may rewrite galaxies, but there are phenomena out there that rewrite the laws of physics themselves, at least temporarily, in their immediate vicinity, before the universe hastily restores order. If quasars are gravity's symphonies, what comes next is gravity's primal scream.
The numbers tell the story. A quasar at 10% efficiency is gravity operating within strict thermodynamic bounds. Respectable, even elegant. But compress a solar mass into 3 kilometers and efficiency becomes meaningless. The gravitational field strength exceeds 1012 g. Escape velocity reaches half the speed of light. Matter stops behaving like matter. Neutron stars and pulsars, that's where the universe drops all pretense. Densities of 1014 to 1015 grams per cubic centimeter. Magnetic fields 1 trillion times Earth's. Rotation periods measured in milliseconds. The Chandrasekhar limit draws a hard line at 1.4 solar masses for white dwarfs. Cross it, and electron degeneracy pressure fails catastrophically. We've been discussing cosmic engines that reshape galaxies. Now we turn to cosmic engines that reshape spacetime itself.
Picture those Cold War strategists, so consumed with terrestrial paranoia that they inadvertently became cosmic explorers. The Vela satellites, named after the constellation meaning sails of the ship, were launched to catch Soviet nuclear tests, yet they caught something far more profound: the universe itself detonating. There's something beautifully absurd about military scientists in 1967 poring over classified data, realizing these gamma-ray flashes weren't from any earthly adversary, but from somewhere else entirely. For years, this knowledge remained locked in filing cabinets marked secret, while the cosmos continued its spectacular light show, indifferent to our security clearances. When Ray Klebersadel finally announced those first 16 cosmic gamma-ray bursts in 1973, he transformed nuclear surveillance into astrophysics. The data showed flashes coming from random directions across the sky, ruling out the Sun, Earth, or any terrestrial source. Imagine the bewilderment. These weren't Soviet bombs, but cosmic firecrackers of unknown origin and distance.
The detection constraints were severe. Those early Vela satellites used simple omnidirectional gamma-ray detectors, yet they achieved millisecond timing precision across multiple spacecraft. The triangulation required synchronized clocks and careful calibration. The raw numbers immediately posed fundamental questions. Even the weakest detected bursts released around 1042 ergs in gamma rays if they were galactic. But if cosmological, as the isotropic sky distribution suggested, we'd need energies approaching 10^54 ergs. That's converting an entire solar mass into pure energy in seconds. The engineering precision was remarkable from the start. These weren't random electromagnetic noise, but structured events with clear onset times, spectral evolution, and definite endpoints. The shortest bursts lasted milliseconds, the longest several minutes. Something in the universe was generating coherent, intense gamma-ray emission on these timescales.
The universe has a wicked sense of humor, doesn't it? Here we were, so terrified of each other's nuclear arsenals that we built eyes in the sky to catch the flash of forbidden tests, only to discover the cosmos had been setting off bombs that make our H-bombs look like birthday candles. There's a profound lesson in how our instruments of suspicion became telescopes of wonder. The very satellites designed to enforce nuclear treaties instead revealed that nature herself violates every treaty we might imagine about the limits of power. We built tools to watch each other and accidentally started watching eternity explode. But perhaps most telling is this 30-year mystery that followed. For 3 decades, astronomers argued whether these flashes were cosmic neighbors or distant strangers. The isotropic distribution suggested vast distances, but the energies that implied seemed impossible. How could single events outshine entire galaxies? The 30-year mystery crystallized into one of astronomy's great debates. Picture April 1995, deliberately staged on the 75th anniversary of Shapley and Curtis, arguing about the scale of the universe, where Donald Lamb and Bohdan Paczynski squared off over gamma-ray burst distances. Lamb championed the galactic halo model. These were neutron star flares within our Milky Way, perhaps 100,000 light-years away. The energies would be manageable, the physics familiar. Paczynski argued for cosmological distances, billions of light-years, which demanded energies that strained credibility but explained the perfectly isotropic sky distribution. Each camp marshaled evidence. No observed repetition suggested one-time cataclysms. The isotropy fitted either a very extended halo or truly cosmological origin. The stalemate persisted until technology intervened. In February 1997, Beppo Sachs pinpointed GRB 97228 with arc-second precision, enabling rapid follow-up that caught a fading X-ray afterglow. Then came the breakthrough, GRB 970508 in May 1997. Within hours, telescopes worldwide captured its optical afterglow. The spectrum revealed absorption lines at redshift 0.835, nearly 5 billion light-years away. The cosmologists had won.
That single redshift measurement transformed the field overnight. A burst at z equals 0.8 with observed fluence of 10.6 erg/cm² implies an isotropic energy release of 3 times 1053 ergs, comparable to the Sun's rest mass converted entirely to energy. The follow-up observations revealed power law afterglow decays, F(T)² 1.2 in X-rays, consistent with synchrotron emission from relativistic shocks interacting with circumstellar medium. The afterglow spectrum showed the characteristic synchrotron breaks, confirming theoretical predictions. Global telescope networks coordinated observations across wavelengths. We learned these afterglows fade predictably, bright initially, then dimming by orders of magnitude over days to weeks. The detection rate jumped from a few per year to hundreds annually as Swift and other dedicated satellites came online.
The resolution in 1997 wasn't just about distance, it was about scale. Suddenly, we understood that the universe operates at energies that make our earthly catastrophes look quaint. When Paczynski was vindicated and these bursts proved cosmological, we had to reckon with a cosmos far more savage than our philosophies had prepared us for. The static, clockwork universe of earlier centuries gave way to one where entire solar systems worth of matter could be converted to pure light in seconds. We weren't just discovering new astronomical objects. We were learning that creation and destruction dance together at energy scales that dwarf our solar system. The universe had been staging these spectacular finales for billions of years while we remained blissfully unaware, trapped in our parochial concerns about terrestrial conflicts.
The numbers reveal physics at breaking point. Take GRB 990123. Its isotropic energy was 310-1054 ergs. That's 3 solar masses converted entirely to energy if the emission were spherical. Even with beaming corrections for a 4-degree jet, we're still talking 1052 ergs of real energy released in under a minute. The jet dynamics require Lorentz factors around 100 to 1,000 just to avoid photon-photon annihilation. At those speeds, matter achieves kinetic energies that compress relativistic physics into milliseconds. The magnetic fields threading these jets must be precisely tuned, strong enough to collimate across thousands of light years, but not so strong they choke the flow. The spectral signatures reveal non-thermal processes. Band function fits show-broken power laws with peak energies from hundreds of keVs to several MeV. Long GRBs average around 300 keV, while short bursts often reach into the MeV range. That's synchrotron radiation from electrons spiraling in magnetic fields at relativistic speeds. The jet opening angles cluster around 5 to 20 degrees. Maintaining this narrow collimation across parsec scales requires extraordinary precision. It's like firing a laser pointer from Earth to Proxima Centauri and keeping the beam within the orbit of Jupiter.
The mathematics of annihilation becomes philosophy when you realize what it means. The universe has discovered how to turn matter itself into pure message. These jets threading the needle between coherence and chaos at relativistic speeds, they're demonstrations of how creation and destruction dance at the very edge of what space-time permits. Consider the profound irony. We've mapped these relationships, catalogued the correlations between energy and hardness, measured jets down to their precise angles. Yet for all our equations, we remain profoundly vulnerable to this cosmic lottery. The Amati relation might govern how stars die spectacularly, but it offers cold comfort to any biosphere caught in the crosshairs. These bursts represent the universe at its most honest. No slow decay, no gradual dimming into irrelevance. When massive stars choose this exit, they broadcast their demise across billions of light years, ensuring their death cry outlasts their birth by eons. In a cosmos where most things fade quietly into darkness, these rare events insist on making their endings matter more than their entire existence. The universe saves its most eloquent poetry for its most violent moments.
The afterglow physics reveals clean mathematical relationships. Synchrotron emission from relativistic electrons produces power law decays. Ft-A, with typical decay indices I equals 1.0 to 1.5 depending on observing frequency and time since burst. The standard model predicts specific relationships between spectral index beta and temporal decay A. For electrons with energy distribution NEP, we get AVA equals 3p-2 or 4, or 3p-3, 4 depending on whether we're above or below the synchrotron frequency. With typical p 2.2, this gives AFBA 1.2 or 0.95. Jet breaks appear when the relativistic beaming cone widens beyond the jet opening angle. The light curve steepens by approximately delta equals 1, so Ft-1.2 becomes Ft-2.2. This transition time constrains the jet opening angle through simple geometry. Then came GRB 7087A in 2017, the breakthrough that launched multi-messenger astronomy. We caught gravitational waves from merging neutron stars, then 1.7 seconds later, the gamma-ray burst arrived. The energy was modest, about 5×10^46 ergs, but we finally had a direct progenitor confirmation for short GRBs.
The merger that spoke in two tongues, gravity and light. Here we have the universe's most profound demonstration that destruction and creation are merely different verses of the same cosmic song. Those neutron stars spiraling together for millions of years, whispering gravitational waves that crescendoed into a scream. Then that flash of gamma rays announcing the birth of elements heavier than iron. The gold in wedding rings, the platinum in catalytic converters. These mundane objects carry within them the memory of neutron stars dying in each other's arms. Every heavy element becomes a fossil of violence, a relic of collisions so extreme they remake the periodic table itself. But perhaps most profound is this. For the first time in human history, we didn't just see cosmic destruction, we felt it. Those gravitational waves literally stretched and compressed the Earth, made us participants rather than mere observers. The universe reached out across 130 million light-years and physically touched us, reminding us that we're not watching from outside, but dancing within. Multi-messenger astronomy revealed that we've always been part of the performance, our atoms forged in these very furnaces we now study.
The technical achievement masks an uncomfortable truth. We've built detectors sensitive enough to measure space-time distortions smaller than a proton's width, yet we remain blind to most bursts. The Swift satellite catches maybe 100 long GRBs per year, but correcting for beaming angles, the actual rate is closer to 1,000 per day throughout the observable universe. Short bursts from neutron star mergers are even more elusive. GRB 7087A was special because it happened nearby, just 130 million light-years. Most short GRBs occur at redshifts around 0.5, half a billion light-years or more. We only detect the ones whose jets happen to point at Earth, a cosmic coincidence with odds around 1 in 1,000. What keeps me up at night is the selection bias. We study the bursts we can see, but the universe's most extreme events might be the ones whose jets miss us entirely. Dark GRBs, orphan afterglows, failed jets. There's an entire taxonomy of cosmic violence we're only beginning to glimpse through gravitational waves and theoretical models.
The selection bias becomes existential dread when you realize what it truly means. We're not just missing data points. We're playing cosmic roulette with extinction-level events we can't even see coming. Those 1,000 daily bursts, each one a potential civilization ender if it happened within our galactic neighborhood, and we only glimpse the ones that happen to wink in our direction. But perhaps our blindness serves as its own dark gift. Imagine knowing, truly knowing, every nearby star that might collapse tomorrow into a gamma-ray cannon pointed at Earth. Would we build differently? Love differently? Or would we simply add cosmic anxiety to our already overburdened psyches? There's something almost merciful in our ignorance, this inability to see most of the universe's violence until it's billions of years past and light-years distant. Yet here's the profound paradox: the very atoms that make our detection equipment, that constitute our fragile bodies worrying about extinction, they exist only because previous worlds were annihilated in these same violent events. We are literally made of ancient catastrophes, using the products of old destructions to fear new ones. Every telescope pointed skyward searching for threats is built from the ashes of stars that died before Earth was born. We're not separate from this violence. We're its children, temporarily organized into patterns capable of recognizing our own impermanence.
The Lorimer burst sat unnoticed in Parkes telescope archives for 6 years. A graduate student found it while mining old Pulsar survey data, this single 5-millisecond radio flash that didn't match any known phenomenon. The dispersion measure was 375 parsec per cubic centimeter, way beyond our galaxy's contribution.
6 years that burst waited patiently in the data vaults, like some cosmic message in a bottle washing up on digital shores. The skepticism that greeted Lorimer's announcement was entirely warranted, and rather instructive about how science actually works. Consider the context. Radio astronomers had been burned before by spurious signals. Those infamous peritons at Parkes turned out to be microwave ovens opening mid-cycle. Imagine the embarrassment. So when someone claims they've found an entirely new cosmic phenomenon based on a single 5-millisecond blip, well, extraordinary claims demand extraordinary evidence, and one lonely burst hardly qualifies. The philosophical tension here is fascinating, between the conservative impulse that protects science from false positives and the openness required to recognize genuinely novel phenomena. For years, FRBs inhabited this liminal space between instrument error and cosmic revelation.
Right, the peritons were a cautionary tale, but the Lorimer burst had fundamentally different characteristics. The dispersion sweep followed the exact frequency-squared relationship predicted by plasma physics. A microwave oven can't fake that precise mathematical signature across 288 megahertz of bandwidth. The key was the dispersion measure itself. Our galaxy contributes around 200 parsec per cubic centimeter along that sightline, but this burst showed 375. That excess dispersion meant the signal traversed intergalactic plasma. You can actually calculate the distance from the free electron column density. Plus, the brightness temperature exceeded 10 core 37 Kelvin. That's not just high, it's physically impossible without coherent emission processes. No terrestrial interference source generates coherent radiation at those temperatures.
Those technical signatures were indeed compelling, yet the community's wariness persisted for years. And that tension between evidence and acceptance reveals something profound about how we construct scientific reality. Even with that impossible brightness temperature staring them in the face, astronomers demanded repeatability, independent confirmation, the whole methodological apparatus. This very conservatism, which initially blocked recognition of FRBs, is precisely what makes their eventual acceptance so powerful. Science moves like a ratchet, slow to advance, but once it clicks forward, there's no going back. Those 4 years between Lorimer's discovery and Thornton's confirmation in 2013 weren't wasted time. They were the crucible in which a new cosmic phenomenon was forged into accepted fact. This episode hints at a deeper epistemological puzzle. How many other Lorimer bursts might be lurking in our archives right now, dismissed as noise or instrumental artifacts? The universe had been screaming these millisecond messages at us for who knows how long, and we only started listening because one graduate student decided to look where everyone else had already looked, but differently.
The systematic response actually validates that caution. After Lorimer, we didn't just wait around. We built dedicated FRB search pipelines. Chime alone now detects multiple bursts per day with its 24-beam digital backend processing 400 megahertz of bandwidth in real time. The numbers tell the story. Pre-2013, we had 4 questionable detections. By 2018, we'd cataloged 60. Today, it's over 800. That exponential growth came from methodical improvements, better RFI rejection algorithms, wider frequency coverage, and most crucially, real-time detection systems that could trigger follow-up observations. What really cracked it open was catching repeaters. FRB 121102 changed everything by bursting over 1,000 times, letting us pinpoint its host galaxy and measure that extreme rotation measure of 10 to 5 rad per square meter. You can't fake a magnetoionic environment that dense.
The repeater was the game changer, not just technically but psychologically. One burst could be anything, but a cosmic lighthouse flashing hundreds of times from the same spot 3 billion light-years away? That's nature announcing herself with unmistakable clarity. Even after FRB 121102's theatrical performance, some holdouts muttered about exotic interference patterns. The journey from Lorimer's lonely burst to today's daily harvest illuminates how scientific consensus actually crystallizes. It's not the linear progression we pretend it is in textbooks, more like a phase transition where skepticism suddenly flips to acceptance once some critical threshold is crossed. With FRBs, that threshold wasn't just about evidence accumulating. It was about our imaginations catching up to what the universe was telling us. Consider the deeper pattern here. Pulsars in 67, gamma-ray bursts in the 70s, now FRBs. Each time, the cosmos reveals another mode of extreme behavior we hadn't even conceived of. Makes you wonder what other forms of cosmic expression we're still deaf to, doesn't it? Perhaps right now, some phenomenon is patiently tapping at our instruments, waiting for the next graduate student with fresh eyes to notice its particular rhythm.
The pattern holds. Each discovery pushes us toward more extreme physics. Pulsars revealed matter at nuclear density. Gamma-ray bursts showed us relativistic jets. Now FRBs demand coherent emission mechanisms that shouldn't exist. The brightness temperatures alone break conventional physics. We're talking 1035 to 1037 Kelvin. That's not just hot, it's beyond any thermal process in the universe. The only way to generate that is bunched charges radiating in phase, probably in magnetic fields exceeding 10^14 Gauss. Here's what keeps me up at night: the energy budget. A single millisecond burst releases 10^38 to 1040 ergs in radio alone. That's a significant fraction of our sun's entire output, compressed into a thousandth of a second, beamed from something smaller than Manhattan. Whatever's doing this has to be the most efficient radio transmitter in the cosmos.
Nature operates at the very edge of what physics permits, like a virtuoso playing at the limits of their instrument. That technical vindication in 2013 carried profound weight. Picture Dan Thornton and his team at Parkes, knowing they're sitting on data that could either revolutionize astrophysics or embarrass them as the latest victims of terrestrial interference. Those 4 bursts they found weren't just detections. They were redemption for Duncan Lorimer, validation for everyone who'd endured the raised eyebrows and knowing smirks at conferences. Science textbooks love their eureka moments, but real discovery often feels more like wandering in a fog of doubt until suddenly the landscape becomes clear. The profound irony is that while astronomers were still debating whether FRBs were real, the universe had been conducting this millisecond symphony all along, thousands of times per day across the entire sky. We'd built all these magnificent instruments to peer deep into space, only to miss the cosmic fireflies flickering right under our noses, because we didn't know how to look for something that brief, that bright, that seemingly impossible.
That vindication in 2013 was just the opening act. The real revolution came with Spittler's team catching FRB 121102 in the act of repeating. Suddenly, we weren't dealing with cosmic explosions, but engines. Persistent, reusable engines capable of firing off these impossibly bright pulses again and again. The numbers from 12102 are staggering. Over 1,000 bursts and counting, sometimes clustering with over 100 detections in a single day. Each burst releases roughly 10^38 ergs, yet the source keeps going. That tells us the energy reservoir must be at least 10^42 ergs. You need a Magnetar's magnetic field to store that much power. What sealed it was measuring that rotation measure of 10^5 radians per square meter. That's not just passing through some diffuse plasma. That's a source embedded in an extraordinarily dense, magnetized environment. We're talking about magnetic fields of milligauss strength and electron densities around 10^5 per cubic centimeter. The only thing that generates environments like that is a young neutron star.
The 2017 localization was magnificent. Not just the technical feat of triangulating a millisecond flash from 3 billion light-years away, but the sheer audacity of building instruments precise enough to catch cosmic lightning in a bottle. And once we could actually to where these bursts lived, the floodgates opened. But here's what truly staggers the imagination. Those early estimates suggesting thousands of FRBs crackling across our sky every single day. We'd been living beneath this invisible fireworks show for all of human history, blissfully unaware that the universe was conducting a perpetual percussion section in radio frequencies we'd only just learned to hear.
Those thousands of daily bursts represent a staggering energy budget we'd completely missed. If even a fraction are as energetic as 12102, the universe is converting 10^42 to 10^43 ergs per day into coherent radio emission. That's equivalent to detonating every star in a small galaxy, just in millisecond radio flashes we couldn't see. The localization changed everything because suddenly we could measure distances through dispersion. Each burst's radio waves get stretched by every electron between us and the source, giving us a cosmic yardstick. At typical distances of 1 billion light-years, these sources are pumping out power that would be visible across the observable universe if it were in optical light. The mechanism's repeatability is remarkable. We're not watching things die. We're seeing engines that can fire thousands of times without destroying themselves. That demands a power source that can tap magnetic energy repeatedly, probably through crustal fractures or magnetospheric instabilities in neutron stars with fields approaching the quantum critical limit. The universe had been screaming at us in radio for millennia, and we'd only just built ears sensitive enough to hear it. Now that we can listen properly, we're discovering that extreme physics isn't rare. It's happening constantly, turning the cosmos into a laboratory for conditions we can't even dream of creating on Earth.
Those brightness temperatures you quote transcend mere heat. Their nature composing in frequencies beyond the thermal, where coherence itself becomes the medium, and conventional physics breaks down entirely. It's as if the universe decided to demonstrate that our intuitions about what's possible are merely the kindergarten primer to a cosmic curriculum we're only beginning to glimpse. And then these impossible flashes reveal their second act, becoming cartographers of the invisible. Each burst's dispersion measure traces every electron it kissed on its billion-year journey, transforming these millisecond screams into surveyors' chains that map the missing baryons between galaxies. We went hunting for new explosions and accidentally found a tool to weigh the vacuum itself.
That dispersion measure insight is precisely why FRBs shifted from curiosity to cosmological tool. When we measure DM values of 300 to 800 parsecs per cubic centimeter, far exceeding our galaxy's contribution, we're directly counting electrons across intergalactic space. Each burst becomes a probe that samples a different sightline through the cosmic web. Some of the most distant FRBs show dispersion measures exceeding 3,000 parsec per cubic centimeter, likely originating at redshifts approaching 3. These single millisecond flashes have traveled through 11 billion years of cosmic evolution, accumulating delays from every ionized atom along the way. We're using magnetar hiccups to weigh dark matter halos, but the coherence requirement still floors me. These sources achieve brightness temperatures up to 10 Thor 37 Kelvin through bunched particle emission. Charges moving in lockstep to create these impossible flashes. The emission region must be smaller than 300 kilometers, probably accelerated to relativistic speeds to avoid self-absorption. We're watching nature operate at the absolute limits of electrodynamics. The fact that some repeaters show periodicities, like FRB A916's 16.35-day cycle, suggests these engines might be modulated by orbital mechanics. Picture a magnetar in a binary system, its burst window controlled by stellar winds or tidal forces. Even at these extremes, celestial mechanics still governs the show.
A 16-day orbital heartbeat governing millisecond chaos. Even in this realm of broken physics, the ancient dance of gravity still choreographs the performance. Nature's most violent percussion section keeps time to the same celestial metronome that guides planets and moons. These magnetar lighthouses don't just illuminate their immediate surroundings, they've become cosmic census takers, weighing the invisible scaffolding between galaxies with each flash. From hunting for new explosions, we've stumbled into cartography of the void itself.
FRB 112-1102's rotation measure of 100,000 radians per square meter obliterates any magnetic environment we've cataloged in our galaxy. That's 10,000 times stronger than typical pulsar nebulae. This plasma must be extraordinarily dense and magnetized, probably a young magnetar's wind bubble with field strengths approaching a milligauss at parsec scales. The polarization stays nearly perfect through this magnetic gauntlet, meaning we're seeing organized field structures that maintain coherence despite the chaos. What really challenges our models is finding these bursts in wildly different neighborhoods, some in star-forming regions, others in quiet elliptical galaxies, suggesting either multiple formation channels or magnetars arising through pathways we haven't considered. The diversity mirrors what we saw with gamma-ray bursts before realizing they came from both collapsers and mergers.
Those field strengths beg a comprehension. We're witnessing magnetic cathedrals that would rip the iron from your blood at interstellar distances. This diversity of cosmic neighborhoods hosting FRBs suggests something more unsettling. Perhaps these aren't death throes at all, but the universe experimenting with extreme physics wherever conditions permit, from stellar nurseries to galactic graveyards. The interferometric revolution that caught these phantoms transformed astronomy itself. We built arrays spanning continents just to triangulate millisecond whispers from the edge of time. Each localization doesn't just solve a mystery, it births a new cosmological instrument. We started chasing radio ghosts and ended up with precision tools that can weigh the universe between galaxies, trace magnetic field lines across billions of light years, and map the cosmic web's invisible architecture. The briefest signals carry the longest memories, each burst a palimpsest recording every electron, every magnetic field, every twist of spacetime it encountered since departing its source when Earth's most complex life was still single-celled.
Those magnetic field measurements are rewriting our physics textbooks in real time. We're measuring field configurations that our models said couldn't exist, yet there they are, maintaining perfect coherence across parsec scales. It's like discovering nature has a whole secret chapter on extreme physics that we never even suspected.
The universe keeps its most audacious secrets in plain sight. We built these continent-spanning ears to eavesdrop on cosmic whispers, only to discover nature has been shouting impossible physics at us all along. We simply lacked the temporal resolution to hear it. Consider this temporal vertigo. Somewhere right now, as we speak, a magnetar 3 billion light-years away might be unleashing a burst that won't reach Earth until our sun has died. Yet when it arrives, that millisecond flash will carry a perfect inventory of every atom between here and there, a cosmic shipping manifest written in dispersion delays. These bursts forced us to confront our own temporal chauvinism. We assumed important cosmic events would unfold on human-comprehensible timescales, supernovae over weeks, pulsars spinning for centuries. Instead, the universe's most energetic radio events happen faster than neurons fire. It's as if we discovered that libraries sometimes explode, broadcasting their entire contents in the time it takes to blink, then fall silent forever.
The transformative power of these discoveries is remarkable. We've turned cosmic microsecond glitches into precision instruments that map dark matter halos, trace magnetic field lines across gigaparsecs, and weigh the missing baryons between galaxy clusters. Each burst becomes a probe fired through the cosmic web, its dispersion delay encoding the density of every electron it passed, turning the universe itself into our laboratory bench. We started hunting for the source of random radio spikes and ended up with tools that can diagnose the health of spacetime itself.
These cosmic whispers become cosmic censuses. Every FRB's dispersion measure tallies up electrons like a universal accountant. We found those missing baryons hiding in the warm-hot intergalactic medium, exactly where theorists suspected but couldn't prove. The universe's accounting ledger was balanced by millisecond chirps from magnetars we'll never see. Contemplate this temporal paradox. A burst lasting 1,000th of a second carries information accumulated over billions of years, each electron along its path adding its tiny signature to the dispersion delay. It's as if the universe compressed an epic novel into a single syllable, yet that syllable contains every word perfectly preserved. These briefest cosmic utterances become the most comprehensive surveys we've ever conducted, mapping matter we can't see, weighing spaces we can't visit, all because some distant magnetar hiccuped and sent a radio pulse careening across eternity to arrive precisely when we'd built instruments sensitive enough to hear it.
The SETI community went absolutely wild when we first detected these. Perfect millisecond chirps with mathematical precision, dispersed exactly as interstellar signals should be. For a brief moment, we thought we'd caught ET's radar ping or some cosmic beacon. Instead, we discovered nature had outdone our wildest engineering dreams, creating coherent transmitters from magnetar storms that put our most powerful radars to shame. That's the profound lesson here. The universe generates phenomena so extreme they masquerade as artificial. We search for alien megastructures while magnetars casually emit signals visible across half the observable universe. If nature can spontaneously create perfect coherent emitters from collapsing matter and twisted magnetic fields, what other impossible physics might be broadcasting right now, waiting for us to build the right ears? The boundary between natural and engineered gets awfully blurry when you're dealing with physics at the Planck scale. Picture a star that's burned steadily for billions of years, suddenly finding itself stretched like cosmic taffy, torn apart by tidal forces so extreme they overcome billions of years of stellar self-gravity. We're exploring tidal disruption events, some of the most violent encounters in the universe. The physics reduces to a simple but ruthless calculation. When a star wanders within the tidal radius of a black hole, the gravitational gradient literally shreds it. That critical distance follows RT, or MB8 m squared 1/3. For our Sun, approaching a million solar mass black hole, that death sentence is pronounced at about 23 solar radii. Cross that threshold and the star's fate is sealed. The disruption happens fast. Stellar matter gets stretched into long streams, half escaping entirely while the other half remains gravitationally bound. That bound material falls back over weeks to months, with peak accretion rates hitting 1 solar mass per year, 50 times the Eddington limit.
That formula captures the exact moment when a star's fate shifts from orbital dance to complete annihilation. The mathematics are unforgiving. For our Sun approaching Sagittarius A, that boundary extends to roughly 1.2 AU between Earth and Mars. Cross that invisible line, and 4 billion years of hydrogen fusion become irrelevant. This represents a fundamental contest between two spheres of influence. The star's own gravitational binding, what's held it together across cosmic ages, suddenly finds itself outmatched by the black hole's tidal gradient. The differential pull across the star's diameter exceeds its binding energy. The side facing the black hole experiences forces perhaps twice as strong as the far side. Consider the existential horror. A star that's burned steadily for billions of years suddenly discovers that the very fabric of space-time has turned predatory. Yet here's where the physics becomes almost perverse. There's a Goldilocks zone of destruction. Black holes below about 1,000 solar masses have tidal radii so small that disruption becomes challenging for Sun-like stars. Above 100 million solar masses, stars get swallowed whole without the dramatic shredding. Only that middle range, the million to 10 million solar mass monsters, provide the perfect conditions for stellar spaghettification.
The energy scales are staggering. When that bound half-solar mass spirals in with 10% efficiency, you're looking at 3 times 10 to the 52nd ergs, enough to power a galaxy's worth of stars for a year. But here's what makes these events so remarkable for observational astronomy. They transform invisible black holes into temporary galactic beacons. Most supermassive black holes sit dormant at galactic centers, effectively invisible until they receive fresh fuel. A single stellar sacrifice can make a previously quiet galaxy nucleus outshine its entire stellar population for months. Swift J644+57 demonstrated this dramatically in 2011. A galaxy that had been unremarkable suddenly blazed with relativistic jet emission visible across the electromagnetic spectrum.
These awakening events reveal something profound about cosmic timescales. A black hole might wait 10,000 to 100,000 years between stellar meals, sitting in darkness like some patient predator. Then suddenly, a single star's fatal misstep transforms that dormant giant into the brightest object in its galaxy. We become cosmic forensic scientists when we observe these events. The light curves become our evidence, the spectral lines our witnesses. Each tidal disruption tells a story. Broad helium emission without hydrogen suggests we caught a red giant that had already shed its envelope. The characteristic T-Quar53 decline in brightness maps directly to orbital mechanics as debris streams return on their Keplerian trajectories. Yet nature refuses to follow simple scripts. Some TDEs launch relativistic jets, transforming stellar funerals into something resembling brief quasars. Others show evidence of partial disruption. Stars that lose mass but survive to orbit again, dying by degrees rather than in one catastrophic encounter. These observational surprises have forced us to expand our models beyond simple stellar execution.
The fallback timescales encode the black hole's fundamental properties. That initial return time scales as T-min MBH 1/2 mice weeks for million solar mass holes, months for 10 million solar mass giants. The subsequent T553 decline creates a distinctive signature we can track across multiple wavelengths. But the real surprise came with the jetted events like Swift J16044+57. X-ray luminosities of 10 to 48 ergs per second, 4 orders of magnitude above thermal accretion predictions. We're witnessing the black hole's rotational energy being tapped through magnetic field threading, launching material at 90% light speed. The rarity, maybe 1% of TDEs produce jets, suggests very specific conditions around black hole spin and magnetic field geometry.
How does one detect a black hole that's been sitting quietly for millennia? Wait for it to commit murder, then analyze the crime scene. Most supermassive black holes remain effectively invisible until they receive fresh stellar fuel. Then suddenly a galactic nucleus lights up like a beacon announcing, "Here I am." The 2011 discovery of Swift J6044+57 epitomized this dramatic awakening. A previously unremarkable galaxy suddenly blazed with jet-powered emission visible across billions of light-years. For months, this single feeding black hole outshone its entire host galaxy of hundreds of billions of stars.
These awakening events serve multiple purposes beyond spectacular light shows. They reveal otherwise hidden black hole populations, turning invisible monsters into temporary galactic beacons. We can measure black hole masses from the peak luminosity and fallback timescales. More remarkably, off-center TDEs might betray wandering intermediate mass black holes, those elusive 10⁴ to 10⁵ solar mass objects hiding in star clusters or galaxy outskirts. The rate statistics tell their own story. Roughly 1 TDE per 10⁴ to 10⁵ years per galaxy, with post-starburst galaxies showing enhanced rates. That connection to merger history suggests these violent stellar encounters trace the dynamical evolution of galactic nuclei themselves.
These cosmic census opportunities fascinate me. We're using stellar death as a surveying tool, mapping the invisible architecture of black hole demographics. Each TDE becomes a probe into otherwise inaccessible physics, revealing not just where black holes hide, but how they've grown over cosmic time. Yet what haunts me about these awakening events is their temporal asymmetry. 10 millennia of patience, followed by months of violent consumption, then return to darkness. It's as if the universe operates on credit. Black holes accumulate gravitational debts over vast timescales, then collect interest through brief but spectacular stellar foreclosures.
The jetted events reveal something profound about energy extraction from rotating black holes. The Blandford-Znajek mechanism can tap up to 29% of the black hole's rotational energy, far exceeding the few percent efficiency of normal accretion. These black holes essentially become cosmic flywheels, storing angular momentum for gigayears until the right stellar trigger unleashes it. The spin threshold, typically above 0.9 in dimensionless units, means these monsters were already primed, their ergospheres threaded with magnetar strength fields. The jet power often exceeds thermal emission by orders of magnitude, proving the black hole itself, not just in falling matter, serves as the energy source.
These rapid spin black holes become cosmic time capsules, their angular momentum encoding every galactic merger, every past accretion episode that ever torqued them faster. Then one star's fatal misstep liquidates giga-years of accumulated rotational history in months of electromagnetic fury. What's remarkable is how we've learned to read these signatures. The spectral evolution tells us about the stellar victim. Missing hydrogen suggests a giant star. Broad emission lines reveal debris velocities. The light curve shape maps the fallback dynamics. We've become archaeologists of stellar death, reconstructing billion-year histories from photons emitted during cosmic executions.
The super-Eddington physics during peak fallback creates conditions impossible to replicate in any laboratory. Peak accretion rates of 1 solar mass per year, 50 times the Eddington limit, drive thermal emission with effective temperatures of 20,000 to 50,000 Kelvin. These systems become natural particle accelerators operating at energies we'll never achieve terrestrially. The circularization process remains poorly understood. How do elongated debris streams shock and dissipate energy to form accretion disks? Simulations suggest relativistic precession causes stream collisions that circularize perhaps 10 to 50% of the mass early, potentially driving massive outflows that carry away energy and explain why some TDEs appear underluminous.
The circularization mystery reveals how even our most violent cosmic phenomena depend on subtle energy dissipation mechanisms. stellar matter stretched into streams must somehow shed orbital energy through shocks and collisions to spiral inward rather than simply orbiting forever in elongated trajectories. This connects to a broader truth about cosmic violence. Even the most dramatic events require precise orchestration. The tidal radius must align with the black hole's mass range, the stellar orbit must achieve the right pericenter distance, magnetic fields must thread the ergosphere with sufficient strength. Nature's most spectacular displays emerge from rather specific initial conditions, not cosmic chaos.
The observational surprises keep coming. Partial disruptions where stars survive to be gradually stripped over multiple encounters. Repeating events that challenge our assumption of one-and-done stellar execution. Some TDEs show evidence of interaction with pre-existing circumstellar material, suggesting these violent encounters occur in already complex environments. The rate dependence on galaxy type also proved surprising. Post-starburst galaxies show enhanced TDE rates, possibly due to recent mergers that perturbed stellar orbits in galactic nuclei. We're learning that stellar destruction traces galactic evolution itself.
These observational complexities reveal that even stellar death admits degrees and variations. Not every close encounter results in complete annihilation. Some stars survive to die slowly, others trigger unexpected jet formation. Still others interact with surrounding material in ways that modify the expected signatures. These events probe the boundary between order and chaos in galactic dynamics. The enhanced rates in post-starburst galaxies suggest that stellar disruption traces the aftermath of galactic violence, merger-driven perturbations that scatter stars into dangerous orbits around central black holes. We're witnessing how cosmic upheavals on billion-year timescales manifest as individual stellar tragedies.
The galactic ecology perspective is crucial. Over a galaxy's lifetime, hundreds of TDEs will occur, not enough to significantly affect stellar populations, but representing a steady channel of black hole growth during quiet periods between major merger events. In dwarf galaxies without other AGN activity, TDEs might provide the only episodes of nuclear luminosity. There's also the intriguing possibility that some close encounters accelerate rather than destroy stars. The Hill's mechanism can launch stars at thousands of kilometers per second. Hypervelocity stars that escape their host galaxies entirely, carrying tales of their violent encounters across intergalactic space.
The Hill's mechanism presents a fascinating alternative outcome for stellar encounters with massive black holes. Instead of tidal destruction, a binary star system can have one component ejected at extreme velocities while the other remains bound. These hypervelocity stars, traveling at hundreds or even thousands of kilometers per second, become cosmic refugees, fleeing their violent natal environments. This reveals the full spectrum of gravitational encounters. Not every close approach results in stellar death. Some produce survivors that carry evidence of their harrowing experiences across the galaxy. These hypervelocity stars become living witnesses to the violent dynamics of galactic nuclei, their extreme velocities serving as forensic evidence of past gravitational trauma.
The velocity measurements of hypervelocity stars constrain the masses of their ejecting black holes with remarkable precision. A star traveling at 1,000 kilometers per second requires a gravitational kick from roughly a million solar mass black hole. Stars moving at 2,000 kilometers per second suggest more massive or binary black hole encounters. These ejected stars also provide a unique probe of stellar populations in galactic nuclei. Most hypervelocity candidates are B-type stars, massive, luminous objects that stand out against the stellar background, but have lifetimes short enough that they couldn't have traveled far from their birth sites at normal velocities. They essentially serve as tracers of violent dynamics in regions too crowded and distant for us to resolve directly.
These escaped stars carry more than just velocity signatures. They preserve chemical fingerprints of their formation environments. Stellar atmospheres can reveal whether they formed in dense stellar clusters, near active galactic nuclei, or in the extreme conditions around supermassive black holes. Each hypervelocity star becomes a time capsule, preserving evidence of conditions in regions we cannot observe directly. The irony is profound. To understand the most extreme gravitational environments, we study the stars that manage to escape them. These cosmic refugees become our messengers from the heart of darkness, their very survival allowing us to probe conditions that would otherwise remain hidden behind event horizons and within photon spheres.
The binary nature of many hypervelocity ejections also provides constraints on stellar dynamics in galactic nuclei. The efficiency of the Hill's mechanism depends on the hardening of binary orbits in dense stellar environments, a process that connects stellar encounter rates to the evolution of massive black hole binaries themselves. Some hypervelocity stars might even carry information about intermediate mass black holes. If a 10 to the 4 solar mass black hole in a dense stellar cluster disrupts a binary system, the ejection velocities would be distinctly different from those produced by supermassive black holes. These objects could serve as tracers of the otherwise elusive intermediate mass black hole population.
The broader picture connects tidal disruption events to the fundamental architecture of galactic evolution. These violent encounters, whether resulting in stellar death or hypervelocity ejection, trace the dynamical history of galactic mergers, the growth of supermassive black holes, and the long-term evolution of stellar cusps around massive compact objects. In this light, both TDEs and hypervelocity stars become complementary probes of the same underlying physics, the response of stellar systems to extreme gravitational environments. One destroys the star to reveal the black hole, the other preserves the star to carry away evidence of the encounter. Together, they provide a complete forensic toolkit for understanding the most violent processes in galactic centers.
Looking forward, the synergy between TE observations and gravitational wave detection opens entirely new avenues for probing extreme gravity. White dwarf tidal disruptions by intermediate mass black holes could produce detectable gravitational wave chirps, while the electromagnetic counterparts would reveal the black hole's location and mass. Large-scale surveys like LSST will discover hundreds of TDEs annually, transforming these rare events into a statistical sample large enough to constrain black hole demographics, stellar cusp evolution, and the rates of various disruption scenarios. We're moving from individual case studies to population synthesis.
These future observations will test our understanding of stellar dynamics in the most extreme environments accessible to astronomy. Do dense stellar cusps around supermassive black holes really follow the theoretical predictions? How do binary black hole mergers affect the surrounding stellar populations? Can we use TDE rates to constrain dark matter distributions in galactic centers? What strikes me most profoundly is how these violent events have become tools for probing the gentler aspects of cosmic evolution. The rate of stellar disruption depends on the relaxation timescales of stellar orbits, the efficiency of dynamical friction, the formation histories of galactic nuclei. We're using cosmic violence to understand cosmic architecture, the universe's most brutal processes, illuminating its most subtle structural principles.
The theoretical implications extend beyond astrophysics into fundamental physics. TDEs probe the strong field regime of general relativity, test our understanding of magnetohydrodynamics in relativistic plasmas, and reveal how quantum effects might emerge at the boundaries between classical spacetime and black hole interiors. Each well-observed disruption event becomes a natural laboratory for physics we cannot replicate on Earth. The combination of extreme gravity, magnetic fields, temperatures, and densities creates conditions that push our theoretical frameworks to their limits, and occasionally beyond them.
Perhaps that's the deepest lesson these events teach, that understanding and destruction can be intimately linked, that some forms of knowledge require the complete annihilation of their subjects. We've learned to read stories of billion-year stellar evolution in the final moments of stellar death, to decode the rotational history of black holes from the electromagnetic screams of their victims. There's something both humbling and disturbing in this realization, that our most profound insights into the nature of gravity, spacetime, and cosmic evolution emerge from watching stars die. We've become archaeologists of destruction, finding meaning in violence, discovering beauty in cosmic catastrophe. The universe teaches its deepest lessons through its most brutal demonstrations.
Consistency of physical law across such extremes provides its own form of cosmic reassurance. Whether a star dies quietly through stellar evolution or violently through tidal disruption, the same fundamental physics governs both processes. General relativity, thermodynamics, and electromagnetic theory remain coherent from stellar cores to event horizons. That mathematical unity underlying cosmic violence and cosmic creation alike might indeed be the most profound discovery, that the universe maintains logical consistency even at the boundaries of existence, even where matter and energy undergo their most dramatic transformations. 1,700 kilometers per second. That's the escape velocity of HVS3, our fastest known hypervelocity star. To put this in perspective, our solar system orbits the galactic center at 220 kilometers per second. The Milky Way's escape velocity at our position is 550 kilometers per second. These stars are moving more than 3 times faster than what's needed to break free from our galaxy entirely.
The first hypervelocity star discovery in 2005 confirmed Jack Hill's decades-old prediction that binary stars venturing too close to our central black hole could be torn apart, with one star captured and the other flung outward at tremendous speed. SDSS J090745 plus 024507, a 3 solar mass B star racing at 1.5 million miles per hour, suddenly transformed theory into cosmic reality. Here was a young, hot star found 100,000 light-years from the galactic center, far beyond where such a star could have formed or survived.
The Hill's mechanism is elegant in its violence. When a binary approaches Sagittarius A star, tidal forces capture one companion while gravitational energy converts to kinetic energy in the other. The math is straightforward. Velocity scales with the square root of the black hole's mass, divided by the binary's separation. For a tight binary with 0.1 astronomical unit separation around our 4 million solar mass black hole, one star could theoretically reach 4,000 kilometers per second, though tidal disruption would likely destroy it first.
These stellar exiles become messengers from the galaxy's most violent region. Each hypervelocity star encodes information about our central black hole's mass, the density of stars in its vicinity, even the orbital characteristics of its former companion. They're like cosmic bottles thrown from the deepest gravitational well, carrying news of conditions we could never directly observe. A star racing toward intergalactic exile at speeds that would cross the continental United States in 3 seconds. It's the universe's own epic of forced migration.
Gaia's proper motion measurements have revolutionized our ability to trace these trajectories. A star moving at 1,000 kilometers per second at 50 kiloparsecs produces a proper motion of just 0.014 milliarc seconds per year. Gaia's accuracy of 0.1 milliarc seconds per year makes detection challenging, but possible. We can now run the cosmic tape backward, tracking 30 confirmed candidates back to their violent origins.
The galactic center becomes a gravitational forge, constantly producing these stellar refugees. Current estimates suggest one hypervelocity star every 10,000 to 100,000 years, rates that align curiously with tidal disruption event frequencies. Each ejection represents a binary system's final moments, where millions of years of orbital evolution culminate in a single catastrophic encounter that rewrites both stars' destinies forever.
The energy budgets reveal the black hole's immense power. Converting orbital binding energy, roughly 10 to the 41st joules for typical binaries, into kinetic energy requires deep gravitational potential wells. A solar mass star at 1,000 kilometers per second carries 2 times 10 to the 48th joules of kinetic energy. Only interactions with supermassive black holes can provide such acceleration efficiently.
There's an optimal mass range for black hole hypervelocity production, what astronomers call the Goldilocks problem. 4 million solar mass black holes like Sagittarius A star are massive enough to accelerate stars to extreme velocities, but not so massive that tidal disruption occurs before ejection. Smaller black holes lack sufficient potential depth. Larger ones shred approaching binaries before they can slingshot one component to freedom.
The disruption also affects planetary systems. Tidal forces strip planets once gravitational gradients exceed star-planet binding energy, typically within a few thousand stellar radii of the black hole. These orphaned worlds face three fates: spiral inward to destruction, remain gravitationally bound to their parent star during ejection, or receive independent velocity kicks that send them on their own hypervelocity trajectories.
Consider the implications. Hypervelocity planets racing through intergalactic space at thousands of kilometers per second, carrying complete geological records from their birth systems. An Earth-mass world at such speeds possesses kinetic energy approaching 10 to the 39th joules, comparable to supernova explosions. These phantom worlds become invisible time capsules, preserving billions of years of planetary evolution, while traversing cosmic voids that separate galaxy clusters.
Gaia's revolution lies in precision astrometry. A 1,000 km per second star at 50 kiloparsecs produces proper motion of just 0.014 milliarcseconds per year, barely detectable even with Gaia's 0.1 milliarcsecond accuracy. This explains why early hypervelocity star discoveries relied primarily on radial velocity measurements from spectroscopy. Only the closest, fastest candidates show measurable proper motions.
Yet, when we can measure both radial and transverse velocities, the power of three-dimensional reconstruction emerges. Suddenly, we're conducting forensic astronomy, tracing stellar trajectories backward through time to identify their launch points. Most confirmed hypervelocity stars trace back to the galactic center, validating the Hill's mechanism. Others point to the galactic disk, suggesting alternative acceleration processes like binary supernova kicks or three-body interactions in dense clusters.
The current census reveals approximately 30 solid hypervelocity star candidates from Gaia data releases. Theoretical models predict roughly 1,000 total in the galactic halo, based on ejection rates of 10 to the negative fifth to 10 to the negative fourth per year. This discrepancy highlights our observational bias toward the brightest, closest examples, essentially sampling only the tip of the hypervelocity iceberg.
Which brings us to rogue planets, the invisible majority. Gravitational microlensing surveys suggest billions of free-floating planets in our galaxy, possibly outnumbering stars. Some formed through direct cloud collapse like failed stars, but many represent planetary system casualties, worlds ejected during dynamical instabilities or stellar encounters. If hypervelocity stars can escape galaxies, so too can their planetary companions.
The energy requirements are substantial but achievable. Accelerating an Earth-mass planet to 1,000 kilometers per second requires 5 times 10 to the 39th joules, comparable to supernova energies. Supermassive black hole interactions or asymmetric supernova kicks in binary systems could provide such acceleration. The result would be hypervelocity planets racing through intergalactic space, completely invisible to current detection methods.
In 2017, our theoretical understanding of interstellar wanderers suddenly became tangible with Oumuamua's arrival, our first confirmed interstellar visitor. Named Scout in Hawaiian, this elongated object passed through our solar system on a hyperbolic trajectory, moving at 26 kilometers per second relative to the Sun. Here was proof that material routinely travels between star systems, carrying information about distant planetary formation processes.
Oumuamua's properties challenged conventional categories. Its extreme elongation, perhaps 10-to-1 length ratio, and non-gravitational acceleration without visible comet activity sparked intense speculation. Proposed explanations ranged from nitrogen icebergs to hydrogen snowflakes, with Avi Loeb controversially suggesting artificial origin. While natural explanations remain most plausible, the object demonstrated how interstellar visitors can expand our understanding of planetary system diversity.
The philosophical implications resonate deeply. Our solar system participates in galactic material exchange, sparse but real commerce between stellar neighborhoods. Oumuamua and Comet Borisov become cosmic messengers, bottles thrown across the galactic ocean carrying news of planetary formation chaos. They challenge our sense of cosmic isolation, revealing that even bound solar systems leak material into interstellar space.
Current encounter rate estimates suggest one Oumuamua-sized object per year passing through the inner solar system. Most arrive with velocities reflecting stellar velocity dispersions, tens of kilometers per second, plus our sun's motion through the galaxy. These represent the low-energy tail of interstellar object populations. Hypervelocity variants moving at hundreds or thousands of kilometers per second would pass too quickly for detailed study.
Which returns us to the detection challenge. A hypervelocity planet crossing our solar system at 1,000 kilometers per second would traverse Earth's orbital diameter in just 2 days, appearing and vanishing before comprehensive observations could begin. We've optimized our astronomical infrastructure for studying objects that maintain predictable positions, not cosmic bullets threading through our neighborhood at relativistic fractions.
Microlensing surveys reveal rogue planets may outnumber stars by significant factors. The 2011 MOA project identified roughly 2 Jupiter-mass free-floating objects per main sequence star, suggesting billions of such worlds in our galaxy alone. These discoveries force revisions to planetary formation theories. Most young systems apparently experience dynamical instabilities that eject some fraction of their planetary population.
The formation scenarios divide into 2 categories. Some rogue planets represent ejection casualties, worlds kicked out during multi-body gravitational interactions or stellar encounters. Others may form like stars through direct cloud fragmentation, but at substellar masses, essentially failed stars that never achieved fusion ignition. Both processes populate interstellar and intergalactic space with invisible planetary populations.
Habitability calculations for rogue planets yield surprising possibilities. A planet with thick hydrogen atmosphere could maintain surface liquid water through greenhouse effects, even without stellar heating. Internal heat from radioactive decay and residual formation energy, combined with atmospheric insulation, might sustain subsurface oceans for billions of years. Earth-mass worlds with appropriate atmospheric compositions could theoretically harbor life in deep crustal environments.
These calculations expand astrobiology beyond traditional habitable zones. Life adapted to deep ocean vents or radioactive environments might persist during planetary ejection, continuing evolution in absolute darkness. Such worlds would become mobile biospheres, carrying terrestrial life through cosmic voids while maintaining internal ecosystems powered by geochemistry rather than stellar radiation. The implications challenge our star-centric view of habitability.
Detection remains the fundamental limitation. Current gravitational microlensing can identify Jupiter-mass rogues, but Earth-mass planets require more sensitive surveys. Projects like the Nancy Grace Roman Space Telescope will improve statistics, but hypervelocity variants moving at hundreds of kilometers per second create detection windows measured in hours rather than days. Most rogue planets remain invisible, carrying whatever geological or biological records they possess beyond observational reach.
Hypervelocity phenomena transform our understanding of galactic ecology. The Milky Way operates not as a closed system, but as a gravitational ecosystem with continuous material exchange. Stars, planets, and smaller bodies flow between systems through various acceleration mechanisms, from supermassive black hole slingshots to asymmetric supernova kicks. This galactic-scale circulation connects individual stellar systems into a broader network of matter and energy flow.
The ejection rate calculations provide quantitative constraints. Hypervelocity star production at 10 to the negative fifth per year, multiplied by average planetary system multiplicities, suggests continuous loss of worlds to intergalactic space. Over cosmic time, this accumulates to millions of rogue planets between galaxies, a hidden inventory of ejected worlds carrying complete geological and potentially biological records from their birth systems.
Supernova kick mechanisms offer alternative acceleration paths. When massive stars explode asymmetrically, companion stars can receive velocity kicks reaching hundreds of kilometers per second. These runaway stars populate the galactic halo with high-velocity objects that, while not reaching intergalactic escape speeds, demonstrate the violence inherent in stellar evolution. Binary evolution becomes a source of galactic material redistribution.
Dark matter mapping applications emerge from hypervelocity star trajectories. Their paths through the galactic halo encode information about the gravitational potential structure. Precision astrometry can constrain dark matter distribution models by tracking how these stellar test particles respond to the galaxy's total mass distribution. Each hypervelocity star becomes a probe of invisible matter architecture.
These cosmic refugees ultimately reveal the universe's dynamic nature. Galaxies continually exchange material through gravitational violence, creating sparse but real connections across vast distances. Hypervelocity stars and rogue planets become messengers carrying information about formation processes, stellar dynamics, and potentially life itself between widely separated regions of space. They transform our perspective from isolated island universes to participants in a galaxy-spanning ecosystem of matter, energy, and information flow. The cosmos reveals itself as fundamentally interconnected, despite the vast emptiness between stars.
Cosmic strings represent one of those beautiful intersections between particle physics and cosmology. These hypothetical defects would be remnants from phase transitions in the early universe, essentially one-dimensional cracks in spacetime carrying enormous linear mass densities, around 10^21 kilograms per meter for the theoretically favored scales. To put that in perspective, a few centimeter segment would weigh as much as Mount Everest.
The weight of Mount Everest compressed into a meter of cosmic thread, physics transmuted into poetry. These theoretical defects embody the universe's imperfection as a philosophical principle. We've journeyed from medieval crystalline celestial perfection to a cosmos that might literally bear scars from its birth. Phase transitions, leaving behind impossibly dense filaments like cracks in cooling glass. The universe carries memory in its very structure, these topological fossils preserving moments when different regions of space couldn't quite agree on which vacuum state to settle into.
The mathematics bears that out precisely. When the universe cooled below critical temperatures, around 1016 GeV for gut-scale strings, different regions chose their vacuum states independently, and where they disagreed, these defects formed with tensions characterized by G-mean values between 10.6 and 10^10, encoding the symmetry-breaking scale directly into their gravitational signatures.
These defects, these mistakes in the cosmic fabric, would be our most direct archaeological evidence of unification physics. Each string would be a frozen moment from when the universe was young enough to manifest symmetries we can only dream of recreating in our particle accelerators. If domain walls had persisted, we might have had a universe partitioned into regions with subtly different physics. Each domain a distinct reality, separated by two-dimensional sheets of exotic energy. Imagine living near such a boundary. Would crossing it change an electron's mass, alter the strength of forces? The fact that we don't see domain walls reveals something profound about cosmic democracy. Our universe somehow coordinated its choices across vast distances, or inflation swept away these catastrophic defects, leaving us in a remarkably uniform cosmos where physics plays by the same rules from here to the edge of observation.
That uniformity constraint gives us hard numbers. Domain walls with gut-scale tensions would have dominated the universe's energy density within microseconds, which is why inflation had to occur after any symmetry breaking that could produce them. The absence of these catastrophic defects, combined with pulsar timing limits placing cosmic string tensions below 10^11, tells us the universe either coordinated its phase transitions with remarkable precision, or inflation swept the slate clean, leaving only the faintest gravitational whispers of these primordial imperfections.
Tom Kibble's crystal analogy from 1976 planted the conceptual seed, grain boundaries forming as materials cool, except scaled to cosmic proportions. These would be archaeological traces of symmetry breaking, fossils preserving the universe's first 10 to 30 seconds when different regions couldn't agree on their vacuum state.
The symmetry-breaking scale relates directly to observability through I-1016 GeVs for G equals 10^6 strings, precisely the grand unified theory energy range. Current CMB constraints from Planck push us below 1.3 × 10^7, while nanograv's pulsar timing achieves G-mean 1.5 × 10^11. We're probing energy scales where unification physics should manifest, yet finding only pristine vacuum.
The universe as cosmic janitor, sweeping away its most dramatic mistakes while leaving just enough traces to tantalize us. We hunt for whispers and shadows, using our most sophisticated instruments to search for what amounts to the universe's birth defects. Every non-detection becomes its own revelation about how exquisitely our cosmos threaded the needle between chaos and sterility. The real philosophical weight lies not in finding these strings, but in what their absence teaches us. That our universe emerged from its violent birth remarkably unblemished, or clever enough to hide its scars beyond our current reach.
The elegance lies in those constraints themselves. Each non-detection sharpens our understanding. Pulsar timing arrays pushing string tensions below 10 to 11 means if these defects exist, they're lighter than 1 part in 100 billion of the Planck scale, encoding phase transitions so delicate they barely disturb spacetime's fabric. Yet even these ghost-like strings would generate gravitational waves with characteristic spectra, turning the universe into a resonating chamber where every oscillating loop adds its voice to a cosmic background hum we're just learning to hear. It's precision engineering at the grandest scale, the universe tuning its own parameters to create a cosmos stable enough for complexity while preserving just enough imperfection to leave detectable traces.
We've built a civilization sophisticated enough to search for flaws in creation itself, yet finding them might reveal we're only here because the universe was nearly flawless to begin with. Every tightened constraint becomes both disappointment and confirmation that we live in a cosmos balanced on the finest of edges, where even the ghosts of ancient symmetries must whisper too softly to disturb our existence.
The mathematics bears this out with startling clarity. A cosmic string network producing gravitational waves at our detection threshold would have tension ratios so precise that even a factor of 10 increase would have prevented galaxy formation entirely. The universe had to tune itself to roughly 11 decimal places of accuracy. We're essentially archaeologists using gravitational wave detectors as our shovels, digging through space-time itself for fossils of symmetry breaking that occurred when the universe was 10 to 35 seconds old. The fact that we can even conceive of detecting something that delicate, remnants carrying less than a trillionth of the Planck scale's energy, represents a kind of technological poetry. Each improved pulsar timing measurement, each tighter constraint from LIGO or future detectors like LISA, pushes us closer to either finding these primordial threads or proving the universe achieved a near-perfect phase transition across its entire expanse.
We find ourselves hoping to discover that reality itself is flawed, while every refined measurement confirms we exist precisely because it isn't. A cosmic catch-22, where our very ability to search negates the likelihood of finding what we seek. We've become sophisticated enough to hunt for the universe's imperfections, only to discover that perfection itself might be the most unsettling revelation of all.
The precision required is almost absurd. If cosmic strings exist below our detection threshold, they'd have to maintain coherent oscillations across megaparsec scales while radiating less energy than a light bulb spread across a galaxy. That's the technical marvel here. We're searching for defects that would have to be so perfectly imperfect they leave gravitational signatures weaker than the universe's own quantum fluctuations. Each null result doesn't just constrain models, it reveals space-time achieved a phase transition cleaner than any laboratory process we've ever managed, across volumes larger than we can properly comprehend.
We've built instruments of such exquisite sensitivity that they can hear the universe whispering about its own birth. Yet what they're telling us is that the cosmos accomplished something no human technology could ever replicate. A phase transition across infinite horizons with near-perfect fidelity. Every industrial process leaves defects. Every crystal has boundaries. Every transformation carries scars. Yet somehow, the universe managed to rewrite its fundamental nature across causally disconnected regions with a precision that makes our finest engineering look like cave paintings. We search for evidence that reality itself stumbled during its most dramatic metamorphosis, only to discover that if it did stumble, it recovered with a grace that defies comprehension. The absence of cosmic strings becomes its own profound statement. Whatever process reshaped spacetime in those first fractions of a second possessed a coordination and coherence that makes even quantum entanglement look clumsy by comparison.
The engineering specifications boggle the mind. We're talking about a phase transition that had to maintain coherence across regions separated by distances light itself couldn't traverse, yet achieved uniformity to better than 1 part in 10^11. It's like asking every atom in the observable universe to spontaneously dance in perfect synchronization without any way to communicate the choreography.
The 2023 Pulsar timing array detections add another layer of intrigue. That nanohertz gravitational wave background could partially originate from cosmic string loops, though supermassive black hole binaries remain the favored explanation. We're witnessing archaeology in real time, sifting through spacetime's resonant frequencies for echoes of primordial defects.
String network dynamics are precisely calculable. Loops move at 0.65 c in root mean square velocity, reconnecting with probability p equals 1 for field-theoretic strings. A typical loop of size L oscillates with period L c, radiating gravitational waves over lifetime t, L, g, me c. Near cusps, string segments approach light speed and generate intense bursts, strain amplitudes of H10 to N21 at 100 Hz for LIGO-detectable events, assuming GM-mol.
The Kaiser-Stebbins effect would manifest as line-like temperature discontinuities in the CMB, temperature discontinuities of order tens of microkelvin for G-mu equals 10 to minus 6 strings. The 2003 double quasar claim offered a tantalizing glimpse of gravitational lensing without time delay, precisely what string geometry predicts, until Hubble's higher resolution revealed conventional lensing.
CMB polarization B modes provide another search channel, with Planck constraining string contributions to less than a few percent of observed anisotropies. The combination of temperature, polarization, and lensing data creates a multidimensional constraint space that leaves progressively less room for string networks to hide while remaining cosmologically relevant.
We're hunting for evidence that the universe failed at something we couldn't even attempt. Imagine orchestrating a symphony where each musician sits in a different galaxy, unable to see or hear their fellows, yet somehow they all hit the same note at the same moment with precision that would shame a quantum clock. We've become capable of measuring the universe's perfection only to find it surpasses not just our technology, but our very conception of what coordination means. Every tightening constraint from our detectors whispers the same unsettling truth. In its moment of greatest vulnerability, when reality itself was rewriting its fundamental rules, the cosmos achieved a feat of self-organization that makes emergence look like child's play. We use our greatest instruments to confirm our cosmic insignificance, not through finding vast scales or exotic phenomena, but through discovering that spacetime itself possesses a capacity for flawless transformation that renders our most precise achievements laughably crude.
That's the technical paradox we can't escape. Our most sensitive detectors, capable of measuring strains smaller than a proton's width across interstellar distances, are telling us the universe accomplished something that violates every engineering principle we know. A perfect phase transition, without communication, without coordination, without error. We've built machines to find God's mistakes, only to discover the humbling truth that if imperfection exists, it's hidden behind physics so clean, it makes our Nobel Prize-winning experiments look like we're banging rocks together.
Our search for cosmic strings has become a mirror reflecting our own limitations back at us with crystalline clarity. We've spent decades perfecting instruments to catch the universe in a moment of imperfection, only to discover that our very conception of perfection pales before whatever process transformed reality in those first impossible moments. The absence of these defects doesn't just constrain our models, it suggests that the cosmos possesses organizational principles so far beyond our understanding that we're like flatland beings trying to comprehend a sphere by measuring shadows.
The numbers themselves become almost religious in their implications. A coordination spanning 1026 meters, achieved to precision of 10 times 11, using no signal, no carrier wave, no central authority. From an information theory standpoint, it's like watching the universe perform error correction on itself without having access to the original code. We measure gravitational wave strains down to 1015, pulsar timing to nanosecond precision, yet these instruments designed to catch cosmic imperfection instead reveal a phase transition so clean it makes quantum error correction look like a child's drawing. The engineering lesson is brutal. Nature accomplished perfect synchronization across causally disconnected regions using physics we can't even theorize, let alone replicate.
Ed Witten's intellectual journey mirrors our collective bewilderment. Initial skepticism about cosmic superstrings surviving cosmology evolved into recognition that fundamental strings could indeed be stretched by inflation from Planck scale to astronomical proportions. The possibility that we might detect particle physics through telescopes rather than accelerators represents the ultimate unification of quantum and cosmic.
Superstring tensions depend on the compactification scale and string coupling. F strings and D strings exhibit different reconnection probabilities. Fundamental strings might have P1, allowing them to pass through each other occasionally, creating denser networks than field-theoretic strings. LISA's millihertz sensitivity window could distinguish between these scenarios through their distinct gravitational wave spectra.
Perhaps that's the cosmic joke hidden in our null results. We've become archaeologists of absence, mapping the contours of a perfection so absolute it reveals the poverty of our own imaginations. The universe didn't just avoid leaving cracks in its foundation. It achieved a metamorphosis that makes our grandest unified theories look like we're still trying to explain fire by rubbing sticks together.
The data becomes almost mocking in its precision. We're pushing detection limits down to strains of 10 to 15, timing pulsars to 100 nanosecond accuracy, yet every measurement returns the same answer: nothing. Think about what that means technically. If cosmic strings exist below our current sensitivity of G mu, less than 10 to 11, they'd have tension so low that a string stretching across the observable universe would weigh less than Earth. We've engineered ourselves into a corner where either the phase transition was perfect beyond any known physical mechanism, or the defects are so weak they're essentially decoupled from reality. The engineering achievement of our detectors has become inversely proportional to our understanding. The better we measure, the more impossible the universe's feat becomes. It's like building a microscope so powerful you discover that atoms arrange themselves with no visible mechanism, leaving us to confront the possibility that space-time itself possesses computational abilities that dwarf anything we call physics.
We've become cosmic Icarus, our instruments growing ever more precise wings that carry us closer to a truth that burns brighter with each approach. The universe achieved its metamorphosis through principles so far beyond our comprehension that even our most sophisticated searches reveal only the shadow of our own ignorance. The greatest discovery hidden in these null results is that we're not just failing to find cosmic strings. We're discovering that reality itself operates on organizational principles that make our proudest achievements in physics look like cave paintings, attempting to capture the symphony's essence.
The technical implication cuts even deeper. We've essentially proven that the universe performed a computation we can't even define, let alone simulate. Every null measurement adds another decimal place to an already impossible feat, coordinating 1028 cubic meters of spacetime to nanosecond precision with no light cone overlap, no information exchange, no detectable mechanism. It's as if the cosmos wrote and executed flawless code across regions that couldn't even know each other existed, leaving us with instruments precise enough to detect our own theoretical bankruptcy.
Our most sophisticated instruments have become mirrors, reflecting back the inadequacy of our deepest assumptions about causality itself. We built these exquisite detection systems, expecting to find the universe's scars, its ancient wounds from birth. Instead, we've discovered something far more unsettling. A coordination so perfect it suggests the cosmos possesses what can only be called anticipatory knowledge, as if the entire universe knew what it would become before the regions could even communicate. It's the difference between finding cracks in a cathedral's foundation and discovering the stones assembled themselves without touching, each one somehow knowing precisely where every other stone would rest across impossible distances. We've become witnesses to our own epistemological limits, using tools of breathtaking precision to measure the shadow cast by principles of organization that may forever exceed human comprehension.
The numbers themselves have become a kind of proof by exhaustion. We've pushed G-mean below 10 to minus 11, which means if strings exist, their energy scale would be 1014 GeV or less, well below where most unification physics predicts defects should form. It's like discovering that water freezes without forming any ice crystals. Except we're talking about the entire observable universe pulling off this trick in perfect synchronization across 46 billion light-years.
We're not just confronting a universe that defied our physics, we're facing one that seems to have possessed a kind of cosmic prescience, a foreknowledge of its own destiny that allowed it to orchestrate this flawless transition. Consider what that means for our entire project of understanding. Every equation we write, every model we construct, assumes causality flows forward through time, that effects follow causes in neat procession. Yet these null results whisper a more troubling truth, that perhaps the universe's organizational principles operate outside our temporal framework entirely, that what we call phase transitions might be merely our limited perception of processes that transcend sequence itself. We've built instruments capable of detecting distortions smaller than an atom across galactic distances, only to discover that the real distortion might be in our assumption that the universe must organize itself through mechanisms comprehensible to minds that evolved to track predators and find fruit. The absence of cosmic strings isn't just an experimental null result, it's a philosophical crisis dressed in the language of particle physics, revealing that our most fundamental category of understanding, causality itself, might be as provincial as a flat Earth model.
The measurement precision has become our confession. We can detect gravitational waves from black holes a billion light-years away, rippling spacetime by less than a proton's width. Yet we can't find a single topological scar from the universe's birth. We've built the most sensitive instruments in human history, only to discover they're perfectly calibrated to measure our own theoretical inadequacy.
We've become cosmic archaeologists, equipped with instruments that could detect a butterfly's gravitational field, yet we're forced to conclude that the universe left no artifacts from its own birth, as if reality itself conspired to erase its own history. What we've discovered isn't just smoothness, but a kind of ontological amnesia, where the cosmos appears to have emerged fully formed, without process, without transition, without the scars that any reasonable physics would predict. The most profound revelation hiding in these null results is that the universe's deepest organizing principle might be its own inscrutability. That incomprehensibility isn't a bug in our theories, but the fundamental feature of existence itself.
The data forces us into an uncomfortable corner. Either the universe conspired across regions that couldn't communicate, or our entire framework of local causality breaks down at cosmological scales. When pulsar timing can track nanosecond variations over decades and still finds nothing, we're not dealing with experimental limitations anymore. We're staring at a universe that apparently solved its own coordination problem through mechanisms that violate everything we think we know about information transfer. The precision of our failure has become the most precise measurement we've ever made.
The universe's greatest magic trick wasn't making cosmic strings disappear, but making us believe they should have existed in the first place. Perhaps we're not failed detectives, but successful witnesses to a cosmos that refuses to be scarred by its own becoming, that maintains its mystery not through complexity, but through an almost aggressive perfection that mocks our need for flaws to understand wholeness.
Our instruments have achieved the theoretical limit of sensitivity. Nanograv can track pulsar timing to 100 nanosecond precision over decades. LIGO can detect space-time distortions of 10 to the 21, yet they find only pristine emptiness where theory demands defects. The numbers themselves have become an indictment. If cosmic strings exist above 10 to 11 in dimensionless tension, we'd see them, but we see nothing. We've reached a point where our null results are more precisely calibrated than most positive detections in the history of physics. The universe hasn't just hidden its scars, it's presented us with a surface so mathematically perfect that the absence itself violates our understanding of how phase transitions must work. Either space-time achieved a coordination that shouldn't be possible, or the very concept of transition fails to capture what actually happened at the universe's birth.
The square-kilometre array promises to extend our archaeological reach through 21-centimetre hydrogen mapping, potentially catching string perturbations in the cosmic web's earliest structures. LISA will survey the millihertz gravitational wave landscape where cosmic string signals might be strongest, while next-generation pulsar timing could push sensitivities even deeper into the theoretical void.
Statistical frameworks using Bayesian analysis weigh cosmic string explanations against alternatives with increasing sophistication. Each improved constraint forces theoretical models toward lower energy scales, driving superstring and field-theoretic scenarios into narrower parameter spaces. The absence of evidence becomes evidence of absence with growing statistical confidence, yet the theoretical motivation for strings remains compelling enough to justify continued searches.
We arrive at the ultimate paradox. Our most sophisticated instruments have become exquisitely calibrated confessionals, where physics admits its own conceptual poverty, revealing not cosmic strings, but the tangled inadequacy of human metaphors stretched across infinity. Perhaps the universe's true topological defect is our stubborn insistence that it must bear witness to its own becoming, when in truth it simply is, perfect, scarless, and magnificently indifferent to our need for narrative. We begin today with perhaps the most humbling fact in all of modern science. Everything we have ever seen, touched, measured, or catalogued represents only 5% of the universe's contents. Stars, galaxies, planets, the very atoms in our bodies, all of it amounts to a cosmic rounding error. 27% is dark matter, 68% dark energy, leaving us swimming in an ocean of the utterly unknown.
The arithmetic is stark. When we map galaxy rotation curves or measure gravitational lensing, we find that every visible structure sits within a dark matter halo several times more massive. A typical spiral galaxy like Andromeda has a total mass of about 1.2 × 10^12 solar masses, with roughly 400 billion solar masses in stars and gas, meaning dark matter comprises about 2/3 of the galaxy's total mass.
This wasn't always accepted wisdom. In 1933, Fritz Zwicky studied the Coma cluster and discovered galaxies moving so fast they should have escaped long ago, unless far more mass lurked unseen. He called it Dunkel Materie, dark matter, and suggested it might consist of exotic particles or unseen gas. But his colleagues weren't ready for such a radical proposition. The idea languished for 40 years, dismissed as the wild speculation of a maverick astronomer.
The revolution came in the 1970s with Vera Rubin's meticulous measurements of galaxy rotation curves. Stars beyond the visible edge of galaxies weren't slowing down as Kepler's laws predicted. They maintained constant speeds, as if embedded in invisible halos extending far beyond the starlight. Galaxy after galaxy showed the same pattern, flat rotation curves demanding unseen mass.
Rubin faced extreme skepticism, as she put it, but observational evidence ultimately prevailed. By the 1980s, the astronomical community had accepted what Zwicky proposed decades earlier. Every galaxy sits within a dark matter halo 5 to 10 times more massive than the visible matter. It's poignant that Zwicky died in 1974, just as the revolution he anticipated was taking shape. His prescient insight, even suggesting gravitational lensing as a detection method, was simply too far ahead of its time.
The anthropic implications are profound. We are composed of the universe's rarest substance, baryonic matter capable of forming complex chemistry. Dark matter doesn't make atoms, doesn't do chemistry as we understand it. It clumps through gravity alone, creating the invisible scaffolding upon which our luminous universe depends. The density profiles reveal extraordinary hierarchies of scale. In dwarf galaxies, dark matter reaches densities of 100 solar masses per cubic parsec in the cores, 10,000 times denser than the Milky Way's halo at comparable radii. Yet when we scale up to galaxy clusters, central densities drop by 20 orders of magnitude, while scale radii expand to hundreds of kiloparsecs.
These gradients read like growth rings in cosmic time, each density distribution preserving the gravitational conditions of its birth epoch. Those ultra-dense dwarf cores assembled when the universe was barely 1 billion years old, space itself compressed, and gravity working with a finer hand. The massive clusters gathered their trillion solar masses during cosmic noon and beyond, when dark energy had already begun its work of cosmic dilution.
The NFW concentration parameter quantifies this temporal encoding precisely. Values around 15 in dwarf halos drop to 5 or 6 in massive clusters. It's a direct mathematical signature of formation epoch written into the density profile itself. The ionosto profile adds another layer with its alpha parameter of 0.17, marking the fundamental signature of hierarchical assembly.
Each dark matter halo becomes a kind of gravitational archive, its density gradient encoding gigayears of cosmic evolution into mathematical parameters we can measure. When gravitational lenses distort background galaxies, they're not just telescopes, but temporal excavators, revealing how the universe's invisible skeleton assembled itself structure by structure.
The precision is remarkable. Weak lensing shear profiles now map dark matter distributions with uncertainties down to 5% for massive clusters. Every gravitational lens becomes a timestamp, every density cusp a relic of cosmic dawn frozen into spacetime's architecture. We can literally watch these profiles unwind in n-body simulations, seeing exactly when each shell of dark matter fell into the potential well.
The universe has compressed not just matter, but memory itself into these invisible citadels, turning cosmology into a form of temporal archaeology where the deepest archives are written in the curvature of existence itself.
Dark energy presents an even stranger puzzle. Here's a component making up 68% of the universe whose equation of state we've measured to W equals -1.01 minus 0.04, yet that precision masks complete ignorance about its nature. We can quantify cosmic acceleration to 12 decimal places, measure the Hubble parameter to 0.5%, yet we have no idea whether we're looking at vacuum energy, a scalar field, or something that would render our wildest theories pedestrian.
We've achieved the precision of accountants tallying a fortune we cannot spend, measuring to exquisite detail the expansion rate of a universe driven by something that might not even constitute a something at all. Dark energy could be the cost of existence itself, the price spacetime pays for the audacity of being. And here we are with our interferometers and supernovae, trying to invoice the void.
The invoicing metaphor cuts deep. We're cosmic auditors discovering that 69% of the universal ledger reads miscellaneous expenses with no receipts. The current deceleration parameter Q equals 0.55 tells us expansion is accelerating at 1.10 square, yet these numbers describe only what dark energy does, not what it is. The equation of state W equals -1 within 5% error bars means we can't even determine if it's truly constant or slowly evolving.
Perfect coordinates for nowhere. What a fitting summation of our cosmic predicament, where mathematical mastery meets metaphysical bewilderment. The Hubble tension adds another layer of mystery. Local measurements give Hz equals 73.2 kilometers MPC, while cosmic microwave background analysis yields 67.4 kilometers per MPC, a 5 sigma discrepancy that might herald new physics or systematic errors we haven't yet understood.
That tension forces us to confront fundamental questions about cosmic evolution. Either our standard model needs modification, perhaps early dark energy raising pre-recombination expansion, or we're missing systematic effects in our distance measurements. Future surveys like DESI and Euclid aim to measure W to 1% precision, but even perfect measurements won't answer whether we're dealing with vacuum energy or something more exotic.
We stand as the universe's most precise mystics, calculating to nanometer accuracy our distance from revelations we may never reach. The cosmos has turned epistemology into an experimental science, forcing us to measure not just what exists, but the exact specifications of what lies beyond measurement.
Weak gravitational lensing provides our most direct probe of dark matter's cosmic architecture. Current surveys like DES and KIDS measure galaxy shear distortions with 0.01 precision, revealing how invisible mass curves spacetime across billions of light years. The technique yields SAL equals 0.770.02 for the amplitude of matter fluctuations, though this sits in mild tension with Planck's value of 0.83.
We've become cartographers of the invisible, mapping continents of dark matter through the subtle distortions they impose on background galaxies. Each lensed arc becomes a gravitational signature, each shear measurement a pixel in our portrait of the universe's hidden scaffolding. The cosmic web emerges not through direct observation but through inference, a vast neural network of dark filaments traced by the light they bend.
The mass scales are staggering. Gravitational lensing can weigh the most massive clusters like El Gordo at 2 pi 10 feet solar masses with 5% precision. Stage 4 surveys, Euclid and the Vera Rubin Observatory, will map dark matter halos across cosmic time with unprecedented statistical power, potentially constraining neutrino masses and testing modified gravity theories.
Each survey becomes a form of cosmic archaeology, revealing not just where dark matter congregates now, but how it assembled across cosmic history. The weak lensing signal traces structure formation from matter radiation equality through the dark energy transition, encoding billions of years of gravitational evolution in statistical patterns of galaxy distortion.
The systematic challenges are formidable: point spread function modeling, photometric redshift uncertainties, intrinsic galaxy alignments. But the payoff justifies the effort. Cosmological parameters measured to percent-level precision, growth of structure tracked across redshift, dark energy's equation of state constrained through geometric and dynamic probes.
Through lensing, we're learning to read gravity's autobiography written in light itself, deciphering how the universe's invisible majority shaped everything we can see. The dark matter paradigm hasn't gone unchallenged. In 1983, Mordechai Milgram proposed modified Newtonian dynamics, MOND, suggesting that gravity itself behaves differently at low accelerations rather than invoking unseen mass. For a time, MOND elegantly explained galaxy rotation curves by altering Newton's laws below a critical acceleration threshold.
The theoretical competition reveals science's self-correcting nature. MOND succeeded with individual galaxies but struggled with galaxy clusters, and failed to explain the cosmic microwave background's pristine fluctuations, which fit beautifully with cold dark matter simulations. Meanwhile, WIMP searches have produced decades of increasingly sensitive null results, despite billion-dollar underground detectors.
This sustained uncertainty showcases the sociology of big science, how research communities maintain momentum across generations of graduate students and postdocs, despite fundamental questions remaining unresolved. Multi-million-dollar collaborations like Xenon and LZ continue refining detection limits, while theorists pivot from supersymmetric WIMPs toward axions and hidden sector particles.
The axion parameter space illustrates the challenge perfectly. Theoretical models predict masses anywhere from 10 stes to 10 pen of p eVol, 20 orders of magnitude, each requiring different detection strategies. ADMX has excluded photon couplings around 10 nem sword GVN in the microelectronvolt range, but that represents a tiny fraction of possibility space.
We're constructing exquisite resonant cavities tuned to frequencies that might not exist, betting careers on particles lighter than neutrinos or heavier than atoms. The enterprise becomes a meditation on persistence in the face of cosmic indifference, where negative results redirect rather than discourage, forcing exploration of ever more exotic corners of parameter space.
Yet the lambda CDM concordance model fits diverse observations remarkably well with just 6 parameters, from cosmic microwave background anisotropies to supernova distances to Big Bang nucleosynthesis. The theoretical framework succeeds even as the physical nature of its dominant components remains mysterious. We have a concordance about quantities we cannot directly detect.
Carl Sagan's famous phrase, "We are made of star stuff," takes on new meaning in a dark-dominated universe. Yes, the carbon and oxygen in our bodies were forged in stellar furnaces, But those atoms represent cosmologically rare matter. We are composed of the universe's 5% minority, the only component capable of complex chemistry, consciousness, and the capacity to contemplate our own cosmic insignificance.
That rarity might explain why we find ourselves in this particular cosmic epoch. Dark energy only began dominating a few billion years ago. We're witnessing the transition from matter to dark energy dominance, from cosmic deceleration to acceleration. It's a temporal fine-tuning puzzle. Why do conscious observers emerge just as the universe enters its dark energy phase?
Perhaps the timing isn't coincidental but necessary. Complex structures like galaxies and solar systems require gravity to overcome expansion, which becomes impossible once dark energy dominates completely. We exist in a brief window between cosmic dawn and eternal acceleration. Observers are rising just as the universe begins its final phase of exponential growth.
The future looks increasingly dark in both senses. As dark energy drives accelerated expansion, distant galaxies will redshift beyond visibility. Eventually, only gravitationally bound local structures will remain observable. The cosmic microwave background will cool and fade. Future civilizations will inherit a universe seemingly empty except for their local group.
They'll face what astronomers call the Great Isolation, cut off from the wider cosmos by dark energy's relentless push. Without access to distant supernovae or the cosmic microwave background, they might never discover cosmic expansion or the Big Bang. They'll inhabit island universes, unaware of the greater cosmos we can still observe.
Which makes our current era uniquely privileged. We can still see the cosmic microwave background, measure cosmic expansion, map dark matter through gravitational lensing. We're the last generation with access to the full cosmic story, living in the brief epoch when the universe reveals its secrets before dark energy closes the book forever.
In the end, perhaps dark matter and dark energy's greatest gift isn't what they reveal, but their enduring mystery, ensuring that future generations will always have fundamental questions to pursue, cosmic puzzles that guarantee wonder never dies, even as the universe grows cold and dark around us.